One, two, one and two.
We have three. Yeah, we have Anna.
One, two, one, two.
Think this.
One and one and two. One, two, one, two, one, two, one and two. One, two, one and two. One, two. Done.
You know, listen, the vibration that not the nothing now. But with me tonight, but now nothing else but what I nothing else, nothing else. Are you girl? Oh, don't, oh, don't, oh, I don't need nothing else. Working hard, but can't even breathe. Sitting is not sleeping, scratching the from my heart, and your body when my feet. You just want to so that hey, But it's exciting. But it's exciting. But it's exciting. Hey, it's cool. It's right. It's right. Shade the line. I've been so down. I'm like drinking out again. Because I from the city. So so funny. Shade the moon. I've been so now I'm like drinking out again. Because I from the city. So so funny. Friends that I should be. They were just hanging on. Yeah. And they now you make the list is a shit. Since we blew up that pain. Place, if I'm rich, I can just one head. Just
is the first scientific session of today about Division B. As you know, Division B is the largest division of the IAU with a lot of different topics. We have 8 different commissions. And this morning, we will have Kevin, and that he will introduce the science and the future of habitable worlds observatory.
Thank you very much. So I'm Kevin Franz from the University of Colorado. I'm going to be giving the talk about the Habitable Worlds Observatory this morning. This is a huge effort by over 1,000 people that are now contributing to the development of HabWorlds. So I'm going to tell you about called the science and the means. So I'll start by a very high-level overview of what some of the key science goals are for HabWorlds. And then talk about the ongoing community efforts that's going to lead into the recently opened NASA project office on HabWorlds, funding our development effort for technology. So let me start with the big picture. What is HabWorlds? So HabWorlds is our next flagship mission, recommended by the Astro 2020 Decadal Survey. It does a little bit of everything. So it's going to carry out a program of transformative astrophysics. I'm showing here galaxy formation at intermediate redshifts with a large UV OIR telescope. It's also the first mission specifically designed to search for the signs of life on Earth-like planets outside the solar system. And here specifically, we're talking about true Earth-Sun analogs. So we would call this Earth 2.0. This is not a rocky planet around a red dwarf, but planets around solar-like analogs. So the outline of the talk today, I'm going to present the overview of the science program. Again, it's very broad, so I'm not going to be able to touch on everything. I'm going to borrow the tagline from John O'Meara, the Big Bang to biosignatures, a little bit of everything. We'll talk about the community effort underway right now to develop the plan for the HabWorlds Observatory. And then I'll wrap up by talking a little bit about the roadmap for the technology development. And this will segue into the next presentation by Dr. Paul Scowen, who's going to talk about technology development for HabWorlds. Okay, so again, where does this come from? So for those of you who aren't familiar, the U.S. Decadal Survey had 3 primary science areas. They were the worlds and suns in context, new messengers and new physics, and cosmic ecosystems. So I won't really go into depth about what any of those are, but the Decadal Survey said that we can do the majority of the key questions in worlds and suns in context and cosmic ecosystems with one large UV-OIR telescope, which we're now calling Habitable Worlds Observatory. So I said the science case is very broad. It pretty much starts with the nearest solar system objects, asteroids, planets, and moves all the way out to high redshift galaxies with pretty much everything in between. So again, I'm not going to be able to touch on any of these in great detail, but let me hit a couple of the key drivers in both of the science areas, worlds and suns in context and cosmic ecosystems. So probably the flagship science case, right, is the search for Earth 2.0. So finding Earth-like planets around other stars. So this is a simulation of the coronagraphic image of the solar system taken at about 10 parsecs away. So we would be able to take family portraits of other solar systems that would look something probably like this. Now we want to take these pictures. We want to we search about 100 nearby habitable zones to find these Earths. But we want to go one step further than that. We want to take spectra of these objects. This is a spectrum of what modern Earth would look like, seen from about 10 parsecs away. There are a few key features which drive us into the wavelength coverage for HabWorlds. So into the optical near IR, there's a search for water. Water itself, of course, is not a biosignature, but we think it's an indicator of a habitable condition. And then the different forms of oxygen that we can search for in the atmosphere. So oxygen is pretty key. So this is modern Earth. This is what tells us that we should be going to look for oxygen. Now this is great, except that Earth did not look like this for most of its inhabited history. So if we want to find Earth over the course of its whole evolutionary history, we need to have an observatory that's capable of doing that. So let me show you here this plot that came out of the Decadal Survey that shows Earth's atmospheric content over time. So starting at the top, that's Earth's formation, coming to the bottom here, which is today. Just focusing on the green oxygen, you see there was very low oxygen in early Earth. The great oxidization event around 2.5 billion years ago gave us roughly 1% level of current atmospheric levels, and then moving on to the current Earth. So this current Earth, which has this very strong ozone and strong molecular oxygen features, only about 13% of Earth's inhabited history. So we probably want to be able to find other Earths that aren't just the modern Earth. So to do that, we're going to need coverage here in the ozone band, around 2,500 angstroms, 250 nanometers. So as the oxygen content decreases, this strongly saturated feature in modern Earth becomes a relatively sensitive tracer for the total amount of oxygen. Now, pushing into the early Earth, when there's not enough oxygen to detect, we think that the best biosignature candidates are these organic hazes that start with methanogenic processes that give rise to strong haze features, again, in the blue near UV. So we want to be able to find these planets. We want to be able to take spectra of them to look for these spectral features that indicate the signs of an active biosphere. Now, we don't just take pictures of habitable planets, right? We're going to get whole family portraits. And so you can go out, and I won't walk through these, but you can go out and find your favorite type of planet around another star, all sorts of angular separations, and really begin to do comparative planetology in a way we're starting to think about with JWST, but really pushing it to an industrial scale. Now, moving on to more broad astrophysics. So we were also interested in how Milky Way-like galaxies come to be. So this is a foggy simulation showing redshift from about roughly about 5 to down to about 2, and you see these small satellites being accreted by the larger central galaxy. I'm going to stop it here in the interest of time. But one of the things you saw, all these protogalaxies coming in. So we want to be able to have the angular resolution to see all of those protogalaxies and understand their properties. Now, jumping ahead a little bit to about a redshift of 1/2, you can see that the spiral disk structure has formed. And now a lot of what you're seeing is the interaction between this circumgalactic medium and the galaxy. So materials getting blown out and then accreted back in. So we want to be able to find both these protogalaxies at high redshift that are feeding the formation, and then understand this interaction at low redshifts. So to understand this interaction, we really want to be able to trace the gas and its strongest tracers, and those all live at ultraviolet wavelengths. So with HabWorlds, we want to be able to trace all the way from neutral hydrogen out to, say, 5 times ionized oxygen, and we want to be able to do it over most of cosmic time. So that really drives wavelength coverage down to about 100 nanometers with the observatory. So you see this is the time starting with the Big Bang here. And over the vast majority of cosmic time, to get these key tracers of the circumgalactic medium and the interaction with star-forming galaxies, we have to be in the rest frame ultraviolet. And this is just a quick example from our data simulations group of what one of these absorption line spectra to a quasar behind one of these galaxies would look like, where you see everything from hydrogen Lyman limit systems, oxygen 6, and even high redshift gas we typically associate with X-rays. So we want to not just be able to have transformative spectral coverage, but we're going to need to have high spatial resolution. So showing kind of the classic angular resolution versus wavelength plot with all of your favorite observatories on it. And just to give you a sense of what these look like at different types of objects at different distances, these are showing, for instance, what some of those dwarf galaxies would look like that were feeding the buildup of large Milky Way galaxies at redshift around 2. So transformative spectral capabilities, transformative spatial angular resolution. Now, we're not just going to do things that are outside the solar system. There's a whole working group. I'll talk about the working groups in a minute on solar system objects. But real-time monitoring of the changing solar system is one of the key goals for HabWorlds, really building on the legacy of Hubble and JWST, which had key planetary science components. Okay, so taken as a whole, what you can think about habitable worlds is kind of like a super Hubble Space Telescope. It's a super Hubble designed to do all of the amazing things that you're used to Hubble doing, maybe about 100 times better, and also being able to find Earth-like planets around sun-like stars. So to do this, we're going to need sizable telescope, and some useful instruments. So telescopes being studied right now are building off the heritage of JWST for segmented apertures. Things being considered are in the range of 6 to 8 meters. I'll say a little bit more about that in a minute. Now, we also imagine 3 first-generation, possibly 4, but 3 for sure first-generation instruments. High-resolution coronagraph. This is how we actually go and find and characterize those planets. A high-resolution imaging camera. This was previously called the wide field imaging camera, and now that Roman's kind of a real thing, we don't call a few arc minutes on a side wide field anymore. And then a multi-object UV spectrograph covering from about 100 nanometers all the way up. And these numbers here that you're seeing are notional right now, and are really being evaluated for the updated science inputs. Okay, so that is kind of the big picture, some of the big picture science that HabWorld is interested in doing. So how are we going to get there? What's the programmatic path forward? So this process started a long time ago with some of the early studies like at LAST and the High Definition Space Telescope study. But most recently, and the most direct inputs came from the LUVOIR and HABEX studies that were conducted ahead of the decadal survey, and many of you are probably familiar with those. And then the recommendation from the decadal survey took those into account, but also things like NASA's Large Mission Study Report and a few other things that I won't go into detail. But essentially, all of these things came together to a recommendation of something that NASA is calling the Great Observatories Maturation Program, or GOMAP. And the idea here was that we wanted to develop the science, the technology roadmap, and have a plan for what these architectures would look like before we got into phase A. So the goal is, so co-develop science, mission architecture, and technology, but said maybe in more plain English, we want to have everything ready to make good decisions when phase A starts, so we can stay on cost and budget with HabWorlds. So the GOMAP process kicked off in 2023. It was broken down by 2 leadership teams. One of them is the Science, Technology, and Architecture Review Team called the START. I won't go through all the amazing things that they did and are still doing, but just the key take home here is that their goal was to quantify HabWorld science goals, right? Take the big picture goals out of the 2020 decadal survey and flow them all the way down into what types of measurements we need to make to accomplish those goals. And then the Technical Assessment Group, or the TAG, this was more of an engineering and hardware focused group. And so their primary task was to study the architecture options and identify the technologies needed to carry out the mission. So there's a flow that you can sort of see here, is that there's one group that's really focused on the science inputs, and then there's a group that's focused on how we take those science inputs and turn it into something that we can build. I'll talk a little bit more about that flow in just a second. So, like I said, this group was selected through a competitive selection process by NASA in about the middle of 2023. This is the START and TAG team at the American Astronomical Society meeting in January. Not to focus on myself, but I was on crutches. I can tell you it's way better to go to a meeting not being on crutches. It's much easier to do everything. Okay. So there's this START and TAG current structure also has a pretty broad international representation, including Anna, who's co-chair of the session. Now this group is growing by the day. This was basically as of a few months ago, but so there's a lot of opportunity for collaboration outside the US. And so how are these groups structured? So the START is focused on a set of working groups that cover a lot of the key science cases. Galaxy growth we talked about, solar system in context, living worlds, a lot of these things we talked about. And then there's the TAG, which is focused on systems engineering, integrated modeling, technology, things like that. And then the joint working groups are where these 2 things meet in the middle, how the science requirements get flowed over to the technical requirements, instrument simulations, and things like that. So the way that you can think about how these different working groups all interface and push towards the ultimate goal of the observatory is in these sets of plots that I'm borrowing from John Zemer, because I think they're a really nice illustration of the issue of the goal here. So the science working groups were tasked with identifying the state of the art, enhancing science, enabling science, and breakthrough science. Now, because they're basically building the left-hand side of the science traceability matrix, they're connecting that with the observation quality. So it's, more observation quality, higher science return. Then the joint working groups take what was on the x-axis and move it onto the y-axis, and then connect the observation quality with what kind of observatory capabilities are required. So better observatory, better observation quality. This gets flown to the technical working groups, which then take, again, what was on the x-axis and move it to the y-axis, and connect the observation quality to the engineering challenge. And of course, you can see where all this is going, that these things all come together and connect the science return to the engineering challenge, right? And that is really the big goal for this near-term process, is to identify what are the science goals and how hard is it going to be to get there. So that's the process that's going now, with the end goal for 2025 being what we call concept maturity level 3, which is basically trade space investigation. So the science cases have been laid out. We have a rough idea about what's required to execute the science cases, and we've explored the technical options to enable that. I gotta skip over that. Okay, so I mentioned that this is laid out in all of these different working group structures. So there are the working groups that are led by a combination of START and TAG members, as well as community folks that are not formally part of the START and TAG. And then a huge number of international participants that are contributing to the individual working group effort. So I'll just show how the team that's doing this is growing over the course of the GoMap process so far. So this is the initial face-to-face meeting that was held about a month after the teams were first stood up. That number doubled to the next meeting that was held a few months later, and that number then doubled again to the meeting that was held at the beginning of this summer. And then in addition to the folks who are here in person, there are over 1,000 people signed up to contribute to these working groups. So it really is a broad international community effort that's leading to the development of the Hab Worlds concept. Okay, so this is where we were up until about a month ago. As of August 1st, there is now what we call the HWO Technology Maturation Project Office, or the TEMPO, that started at NASA Goddard on August 1st. So this is really good. So this is sort of a changing of the process here, moving from the community-focused GoMap process into the project office is really signaling the start of the pre-phase A effort. And yeah, it's a transition from the START and TAG teams. So the project office is taking over a lot of the functions that the GoMap was executing, but a lot of the near-term goals are very similar. All right, the leadership team here, led by Lee Feinberg at Goddard, is the principal architect, and Giada Arni is the interim project scientist. There's a whole list of leadership team folks, so I won't read all of them for you right now. But the goal for essentially the next year or so is to complete the science, engineering, and technical trade space study that was started by the GoMap, and then develop a comprehensive technology maturation plan so we can have the path for all of these things identified before the mission formally starts phase A. Okay, and so that sort of leads to the technology roadmaps. Now, this is something that was developed as sort of a version 1 draft by the existing tag, but is going to be really picked up in earnest by the project office, and something that Paul will talk more about in the next talk. And so some of the technologies, there's pretty much everything that goes from technologies that impact the entire observatory, like mirror coatings, things that are specific to, say, high contrast imaging, like ultra-stable telescope systems and coronagraph design, talking about the test beds and test opportunities to get these things into large facilities to do prototype measurements, or even on small missions for spaceflight testing, and going all the way through to the idea of preparing for servicing the Hab Worlds Observatory at L2 at some point during its, or maybe at several points during its lifetime. So all of these things are part of the technical road mapping activities that are going on now. And so these break down into a couple of key areas. So we've got technology that's related to essentially the entire observatory and the telescope, because the telescope feeds everything. So these would be some of the things that we talked about before, like ultra-stable structures. Originally, HabWorlds was supposed to be an open telescope, but our lessons with JWST have told us it's probably a good idea to protect against micrometeorites. So we're now barrel architectures, all the way through with thinking about how do we actually launch a large telescope like this. Then there'll be technology specific to the high contrast imaging, the coronagraph. So this is coronagraph design, very low background detectors for optical IR spectroscopic follow-up, and then various technology developments about coronographic masks. And then more near and dear to my heart, the UV side, which things we're focusing on are ultraviolet detectors. So large format, low background photon counting detectors covering all the way from about 100 to 400 nanometers. And something that will be new for the ultraviolet, which is multi-object capability. So we've never had a UV multi-object spectrograph in space before. And if I was giving a different talk, I would tell you all the ways that that is amazing. But so this is another area that we're working on. And then these are the places, of course, where all of these things come together. I talked about the UV coatings and ultra-stable mirrors. So the initial TAG working group, we're going to read all of this, and I'm going to ask you all questions about it during the Q&A. Broke these things down into these 3 different categories. Don't read any of these things, but it's basically things that are related to the coronagraph, things that are related to the telescope, and things that are related to the UV instrument. And so you see there are about a dozen-ish of these high-priority technologies that need to be matured. And getting this in place and developing the plan for maturing these technologies over the next 3 or 4 years is really one of the key outcomes of the concept maturity level exercise. So in addition to the individual technologies, one of the things that the TAG has been investigating are things we're calling the exploratory analytic cases. So these are first round studies of mission architectures that will meet the science requirements of the mission. So again, the goal with this CML3 is to really explore the trade space. So these are not going to be the mission that we build, but these are going to be missions that look at different parts of trade space and allow us to decide what's hard, what's feasible, and what types of mission architectures satisfy the science requirements. And one of the key goals here is to basically be able to build end-to-end model architectures at a reasonably fast pace so we can explore this trade space in the timeline allowed. Then again, identify key technology gaps. Some of that's already been done. Some of that's coming out of the EAC process. And then talk about the architectural options and breakpoints. Now, this goes all the way from things like, is this individual component feasible, to is there a launch vehicle that's compatible with this observatory that we develop? But again, I think the key thing here is not to expect that any of these cases are actually going to be the baseline mission. These are just things to practice. And one of the things that Lee Feinberg always talks about is that this is a CML3 version of JWST. Of course, this is not what we build. The CML9 version of JWST looked much more like this. So I think this is we're in this phase right now, seeing what's feasible and what meets the science requirements. What we will build will look something, well, not like that, but something different. So these are the 3 EACs that are being studied right now. They span 6, as I mentioned earlier, they span 6-meter primary apertures to 8-meter primary apertures. They're all segmented telescopes. The first 2 are off-axis designs, and the third one is a slightly larger on-axis design. The on-axis is favorable for some reasons, for some applications, but makes the high contrast imaging a little bit harder. So the telescope is wider as a result. So I won't walk through all of these, but you can see as you there, all of these things, all the way down to how it's going to fit in the rocket, what types of rockets can launch these. Many of these rely on the SpaceX Starship, up to some of these EAC3, which is the only thing that can launch it right now that's projected for the 2030s and beyond as a Starship. So I'm about wrapped up, so the timing is good. So these are the things that are being done right now. EAC 1 has been done. EAC 2 is under study right now, and EAC 3 will be done in the next several months. Okay, so that brings me to my summary. So Habitable Worlds Observatory is being designed to study how common extrasolar planets are around other stars, and then what frequency with which are those planets inhabited. So it's not just the search for habitable. We're not just looking for planets that are in the habitable zone, but which of those show the active signs of a biosphere. So in addition to that, it's going to be able to carry out this sort of 100 times Hubble spectroscopy and imaging that's basically all the rest of astronomy all at the same time. So right now, the project is wrapping up the GoMap phase that was led by the community-driven start and tag teams. This HWO project office at Goddard was just started 12 days ago. You probably didn't think that you were going to be able to see something that was so exciting and up-to-date happen here, so I put Wolf Blitzer on there, but we'll get Wolf Blitzer out of there for now. And then the near-term goals for the project office are to complete the science and trade space investigation, develop the technology roadmap, and develop the path for how we get to the mission confirmation review that's happening ahead of the 2030 decadal survey. So I'll stop there and take questions. Thank you.
We have some question here in the room.
Thanks, Kevin. Great talk. Actually, two questions, if I can.
Sure.
One, you mentioned first generation instruments, so that and I saw serviceability. So maybe you could explain what the vision is for that. And the second question is, in this phase now with the project office, what's the mechanism by which the international community will be involved and contribute to this phase?
Yeah, good questions. So we actually have a congressional mandate to make all future flagship observatories serviceable. So the plan is to absolutely have a second and possibly third generation suite of instruments. Now, people aren't really talking in detail about what that second set of instruments would look like yet, but the idea is that the instrument suite would be modular, so and not require quite the level of human intervention with, say, the Hubble servicing. So that is the plan for that. And then in terms of the shift to the project office, maybe I'll let Paul say a little bit more about that during his talk. But yes, I mean, the project office is actively in discussion with other space agencies outside the U.S. So I should be careful about what I can actually say now. Yeah. I would have 12 days ago, I would have gone totally off script. But now that there's a real project office, I have to be a little more circumspect. Yeah.
You have some question from the more? No question? Okay. So more question here?
Thanks. Nice overview. So, I mean, nobody likes to talk about money, especially, well, ever, but I mean, at this stage in particular. But sometimes having a cost cap actually forces people to make like hard decisions, but the right ones. And so right now, the process you described is kind of like open-ended into, an infinite costing mission. So at what point and it's much harder to descope, right, later on. So at what point does financial reality come into this process?
Yeah, that's a good question. So the financial reality is informing the starting points of the architecture studied right now. If you're familiar with the ABEX and the LUVOIR studies, LUVOIR had a very strong recommendation for 15-meter telescope that the decadal survey said is ridiculous and you will never be able to afford that. We like the science, but is not feasible in our current fiscal environment. So that balanced with the science is why we're starting at 6 to 8 meters. The costing process happens after CML3, but it is something that people are keeping an eye on. So I don't think it is maybe that open-ended because the boundary conditions are starting with the initial constraints that were recommended by the decadal survey.
Thanks.
Yeah.
Some more question? Okay, thanks again. And the next speaker will be Paul, and now we will move to the technical things that will be necessary to obtain this. You can start. What?
Okay,
Okay,
there
thank
we
you.
go. All right, so thank you to Kevin for an excellent primer. A few of my initial slides are now irrelevant because he's already covered it, which is good. So what I'm going to be talking about is this start of the conversation about the technologies that we feel are already informed about what we are likely to need for habitable worlds and ways to get there. In particular, I was asked to talk about the fact that we're already starting this process with CubeSats and smallsats and stuff, but also the larger opportunity for involvement. So a lot of this you've already heard. We already started the process from 2023 with this start and tag process, and what is now evolved into this project office at Goddard, which started on August 1st, is a stand down of the tag, with the project office being staffed exclusively by government folks, and that is deliberate to make sure that everybody involved who was involved in the tag process, who might be someone who wants to bid or provide a particular solution, is now no longer bound by conflict of interest or anything like that. So the idea is to try to maximize the opportunity for folks to get involved by letting the civil servants do the paperwork. So that's where we're going right now, and so I'm going to talk about some of that here today. Now, you've already seen this slide from Kevin, and this is the notional environment for the instrumentation that the various science working groups that you heard Kevin talk about have been exploring. It's not unique in many regards. Indeed, there's some things that have spilled in, like in terms of the multi-object spectrograph at the last face-to-face, we heard a series of convincing arguments that they would like to have an IFU in there as well as a wide field multi-object kind of capability. So something a little bit closer to what maybe NearSpec is doing right now on James Webb. But these are all deliberately being looked at from the science driver perspective rather than the other way around, where you take the technology and say, okay, what can you do with that? So it's a matter of not putting the cart before the horse. It's understanding the science that you wish to achieve with the system, and then looking at the technologies that are necessary to be brought to bear to make that a reality. And so a lot of these ideas here, the wavelengths, the fields of view, these kinds of things, these come out of those studies that Kevin mentioned, the LUVOIR and the HABEC studies. Some of those drivers are very similar. We're running into similar ideas in terms of science for some of the stuff, but let's be real, the science drivers that went into those studies is now already 6 to 8 years old. And we've had James Webb now on orbit for a couple of years. Science has moved forward as you would expect it to, and so the drivers are going to be evolving similarly. So these are some of the things that we're seeking to involve. Now, to touch on something that was just asked about in terms of possible second generation instruments, there's this idea about whether an ultraviolet channel for the coronagraph is something that can be brought to bear for the first generation, or maybe it's better to be done as a second. That's an open question right now, but that's something that's being discussed. But anyway, these are the kinds of things that we're looking at. So we're interested over and above the challenges of the coronography. It's what broader field, not wide field imaging, and it is this multi-object spectroscopy that we're seeking to bring forward. Now, this is the eye chart, or one of the 3 eye charts that Kevin introduced. And a lot of the stuff that you're seeing in here, especially in the coronography, we're worried about the introduction of deformable mirrors, sensing and control, and these very low noise, indeed almost noiseless detectors that are necessary for the spectral characterization of these direct imaging data sets of planets. This is a one particular suite of technologies that they're seeking to advance. There are some very challenging issues on this particular chart. This particular road mapping exercise is being led by Feng Zhao at JPL. Then the next one is related to the ultra-stable telescope issue, which is the business of how stable the mirrors have to be over the course of an integration with these coronagraphs to stop deformation in the wavefront just being introduced by the telescope itself. And then thermal control and potentially the idea of completely isolating the instrument from the observatory. This is an idea that Lockheed Martin has brought forward. So there's a lot of ideas here that are on the table, but the one that I'm going to be talking a little bit more about today is the stuff that's being done with regards to high sensitivity UV and instrument technologies. So it's producing mirror coatings on those ultra-stable mirrors that gives you throughput in the far ultraviolet. It's adopting or learning the lessons of all the technology development that's happened with detectors in the near ultraviolet visible and especially in the far ultraviolet. There's this business of multi-object selection and then producing ultra-low scatter gratings for use in the ultraviolet to beat down the background noise. And these are all areas that are under consideration. You'll notice that this was a little bit longer than the version that Kevin had. This is hot off the presses. This basically came out of the last face-to-face. So what I'm going to be talking to you about is efforts that are ongoing, and these are really just being held up as examples of the way some of the technologies that are relevant to habitable worlds are actually being advanced through relatively small, cheap ways of solving problems with CubeSats and smallsats and suborbital rocketry and things like that. This first one is one that I'm actually part of. This is the SPARCS mission, which is a near and far ultraviolet photometric CubeSat. Now, the advantage of going to these suborbital platforms is that it gives you the keys to the car, right? You get to drive the observatory and sit and park on objects as long as you want. And so that's what's driving the revolution that's going on with these small satellites. But in this particular case, the idea here is to go and park and measure and back out the flaring rate of M-class stars. It's a relatively conventional CubeSat with a relatively conventional telescope. The tricky bit is in the detectors themselves, and that's the technology that this particular spacecraft and observatory is seeking to advance. It's a relatively conventional telescope that feeds a dichroic split so you can image both in the far ultraviolet and the near ultraviolet at the same time. And that's the key here. What we're seeking with this particular mission to advance is to provide flight qualification of detectors that are solid state, that have been delta doped by our partners at JPL to provide sensitivity in the far ultraviolet, and to introduce solar blind or solar blocking filters in the near ultraviolet case as an external filter, in the far ultraviolet case as a filter, a metal dichroic filter that is deposited on the surface of the detector. I can tell you from going through AIT with these detectors, it works really well. It blocks out anything that you try to throw at it to make a flat field. So it works very well. But this is an example of a technology or a suite of technologies that you might seek to leverage to provide capabilities for habitable worlds. And we're going to be flying this thing hopefully as early as March of next year. So that will be a potential opportunity. This next set of slides, I'd like to thank Brian Fleming at Colorado for providing. This summarizes the multivariate way that CU and the larger LASP Institute is bringing to bear to develop technologies through, again, the use of cube smallsats and sounding rockets. So there's a number of different ways that the team that Kevin's part of is developing for the various facets of providing truly efficient UV spectroscopy, but in a low-cost way. So the idea is that some of the things that the folks at Colorado have been involved in is, of course, the development of these new protective coatings. We're very familiar with the kinds of protective coatings that are on Hubble right now. Things like aluminum with an overprotective of mag fluoride, but that unfortunately cuts off your reflectivity at 115 nanometers. And you already saw from Kevin that there's some reason to want to go to 100 nanometers for a number of other diagnostics. One way to get there is to use lithium fluoride, but it's a particularly thorny material to use. But there's this new approach, which is to provide protected lithium fluoride so that the hygroscopic nature of the material doesn't mess you up. And there's a variety of different ways of doing this, and some of them have been explored already by the team at Colorado with some of their suborbital flights, Cysteine and Infuse. And there's a new way of doing this protective overcoat out of Goddard, which uses a xenon precursor. And that new way of doing it, which provides a little bit more stability and is deposited at a lower temperature, is going to be explored in future missions, Infuse and Sprite, out of Colorado. In terms of those UV gratings that I mentioned earlier, there's a number of different groups, Penn State, Johns Hopkins, Iowa, now Central Florida, are going to be exploring ways to use electron beam and other techniques to produce really ultra-accurate, low-scatter gratings for use in the ultraviolet to beat down that background, because the challenge that we have in the ultraviolet is trying to make sure that the noise term goes away as much as possible so that the weak signal that you're seeking to measure, even with a 6 to 8 meter primary, is not limiting you. And this particular technology is being flown on a number of different platforms out of Hopkins, out of Colorado, and these things are showing some real promise initially. And then there's a number of other things. The idea of multi-object spectroscopy, in particular, this idea of integral field. There's number of different ways, number of different challenges there. You can do this potentially using fibers, which has been done with the optical, of course, we're very familiar with, but finding fibers that work well in the ultraviolet is a little tricky. There's a number of technologies that I know the folks at Colorado are exploring. But then another way, of course, in the ultraviolet is to use reflective image slicers. And there's a particular project that came out of there that the leader, Dr. Emily Witt, who's now at Johns Hopkins, I believe, is pioneering and advocating. And so there's a lot of different ways of solving this problem that are being brought to bear through the experience of suborbital flight. And of course, the large format photon counting detectors, these are really starting to get very large and use advances that have come to bear through investment from NASA in things like use of atomic layer deposition to change the materials that you use in the acceleration, in the amplification stage. And this provides greater flexibility when it comes to the passbands and the wavelengths that you might choose to use. And so a lot of good work has been done by Colorado in that regard. Moving on, another group, which is at Johns Hopkins, led by Stephen McCandless. They have a project called Fortis, which is a suborbital rocket that they have flown multiple times. And the promise here is to really kick the tires and demonstrate multi-object spectroscopy in a variety of different ways. And their science drivers are, of course, in this particular case, to pull out individual spectra from around globular clusters to allow them to do some interesting science there. But the drivers that are or the technologies that are being leveraged here is one of the ways of providing these multi-object solutions. One of them is the microshutter array program at Goddard. Another one, which we'll touch on a little bit later, is a micromirror solution. But this particular project flies large object or large area MCP detectors as well, and tries to use the MSA, the microshutter array, to pull off the zero order spectrum. It also leverages investment that has been done in the ultraviolet, certainly in Colorado and other places in France, of using holographic gratings. The idea, of course, in the ultraviolet is you want to minimize the number of reflections you use. So if you could put power in your grating, then that takes one of the reflections out of your system. And of course, the idea of leveraging different ways to coat the mirrors to provide high throughput in the ultraviolet. And this is a graphic of what the suborbital rocket looks like. And Stephen's actually in New Mexico right now, getting this thing ready for a launch. So best of luck to him and his team. And the idea, at least with the micro shutter array program, which I'm actually involved in helping run right now at Goddard, this is advanced beyond what we are currently using on NearSpec with James Webb. That method of commanding and actuating the shutters used a moving magnet. The next generation version of this is purely electrostatically driven, and it has a number of different advantages because of it. One of the things that we're also trying to do in the next generation is make this thing work in the ultraviolet over the infrared, which involves the use of light shields and the better machining and manufacture to prevent diffraction of photons around the edge of the shields, because ultraviolet photons are slippery little devils and they will get around where you don't want them to. So that's part of what we're trying to do with the design of the next generation micro shutters. And of course, the large format MCPs, Fortis is also seeking to advance, and these are actually getting quite big now. Which is really a boon for potential applications that they might be used for. And then here's an example of some of the lithography and different manufacture techniques that they're using to create glazed gratings for the application. And then this is repeating the xenon precursor deposition technique that's come out of Goddard, which is actually right now probably one of the more promising approaches to provide protected lithium fluoride that might be used on a mirror segment as large as 1.5 meters, which is what something like habitable worlds might need. So the final thing I want to touch on is this stamp idea, which is being championed by Kevin, but a bunch of us are involved in different facets of this. The idea, you saw this graphic from Kevin, is to target the particular areas that are really germane to the ultraviolet in terms of coatings, in terms of detectors, in terms of multi-object selection, gratings, and those kinds of things. And so the idea from this approach is to take a lot of the recommendations that came out of one of those working groups that was going on through the GOMAP exercise, and to look at ways to invest beyond these routine APRA and SAT type funded technology investment opportunities to maybe go the next step. The idea to sort of roll it all the technologies you might seek to advance into a single solution. And so the idea is to develop a laboratory prototype environment, and then to actually demonstrate it in space potentially. So the idea, it's modeled on something that Earth Science does, but the idea is to try and leverage and bring all of that to bear with a single solution. And so this idea of a dedicated platform to develop and advance the technologies to float all boats at the same time is the idea behind it. And it provides the opportunity for accelerated development and allows you to test it and fly it in pretty much the way that it would be envisioned to be used on habitable worlds, but in a more modest form factor. And so the idea is that lessons learned from doing this will then immediately inform what you might choose to do with habitable worlds going forward. And so this is the idea behind this approach. So the idea is that this kind of thing could inform the development of future great observatories. It allows you to advance science definition and technology, but it provides an inclusive mission framework that can be used for the development into the near future. But the point is here, it's a separate funding line, so it doesn't eat everybody's lunch when it comes to the SAT and APRAs to allow the technology that is really germane to what providing ultraviolet on habitable worlds looks like, but it does it in a very focused and very efficient way. And so the idea behind the design is to fly a modest-sized aperture and to put all of the things that you care about, near ultraviolet, far ultraviolet gratings, some kind of multi-object selection device, a near ultraviolet and far ultraviolet detector, and of course those optics will be coated with the appropriate mirror coatings of the kind that we've been discussing. And so this particular design has again, the far and near ultraviolet detectors. It has the ability to use the multi-object system to pull out particular spectra from a particular extended target. And there's a number of different ways to get there. We have gratings already that are being flown on McCandless's Fortis that could be leveraged immediately. We could roll these out and deliver them within the next few months. So there's not a huge amount of development involved. It's a matter of demonstration, and that's really what we're focused on here. And then using some of the MCPs that were already flying out of Colorado, but there's also these new ones that are being developed for UVEX that potentially could be leveraged at least from the CMOS family. And the mirror coatings, again, this is the kind of Z-lift type thing that we would coat onto the mirrors themselves. So the approach here is to go ahead and identify your mirror coatings and come up with an initial design and look at this from the perspective of what science and technology is telling you you need to do. You do the deposition, you fabricate and test your mission, and a key focus of this particular program is to train the next generation, the early career folks. HabWorlds is a long way off, and an awful lot of us who are involved in developing it right now, we are not the ones who are going to be using it. It's the early career folks. So we need to make sure that those folks are trained and brought up the curve in parallel with the technologies, for instance. But anyway, incorporation of the lessons learned from the S1 mirror to produce the final advanced lithium fluoride deposition at something like a 0.8 meter size, and then go through the testing and demonstrate environmental stability, and then conduct a mission launch to demonstrate how it works. So let me finish up by just saying that there's an awful lot of different architecture and technology questions and options and possibilities on the table. You've heard a lot about them this morning from Kevin and myself. There are some that we already know about. You've heard about mirror coatings, you've heard about particular detectors, you've heard about gratings. There's a whole bunch of different things there, but that doesn't mean that there's only one way to deliver those particular technologies. Right now, NASA and the project office are very interested in hearing from a number of different folks who might have a way to solve particular problems. We're staying as agnostic as possible to that. We've got different solutions for detectors from Japan, from North America, from Europe. We've got coding options from North America and Spain. There's a whole bunch of different ways of doing this. And right now we are very interested in talking to people about ways they could contribute at the international level to make these things work. I hope I've shown you this morning that there's a lot of work going on already using small sats, CubeSats, and suborbital platforms to try to advance some of those technologies, but there is yet more opportunity to do that. The nice thing about small sats is they have relatively short turnarounds, and what we're seeking to do is advance a lot of these technologies in the very near future. One of the things that we're seeking to do is come up with the architecture and demonstrate the mission concept review before 2030. That's likely to make the ultra-stable mirrors and the coronography technologies get locked in before that. But for the ultraviolet and visible, there may be some fuzz in terms of schedule. So we're open to the conversations at this particular point. So we believe there's ample opportunity for collaboration and contribution from any number of different partners around the world. And we would love to hear from you if you believe you have a solution that should be made available to us. And with that, I will finish up and answer any questions. Thank you.
So, thank you for the very beautiful talk. Do you have, you didn't talk so much about the technology for making the mirrors of the primary.
Yes, because that's not my area of expertise. There are a number of different groups that are already being engaged in the US. Various companies like L3Harris and Northrop Grumman and others like that are looking at the stability of those mirrors. In terms of manufacture, there's a number of different options in terms of the material you might use, of course, from zero door to ULE to various other things. Some of it's got to do with the way you make the mirror. Some of it's got to do with how you lightweight it. Some of it's got to do with how you support it and actuate it. But there's a lot of different possibilities there. And I know that while they are talking to very specific vendors about possibilities, ways to solve that problem, they are open in exactly the same way as I talked about here. They are open talking to different groups about the ways to solve it.
Any other question? Do you have something from remote? No. Okay, thanks again.
Thank you.
The next speaker will be Anna. She will present the European point of view. Oh, yeah.
So, thank you, everybody. I was when I had to put a title to my talk, I was wondering whether I should say European or Europeans. You know, I don't know whether you know about this talk by historians that they say that when they talk about the history of Rome, they talk about the history of Rome. However, when they talk about the history of Greece, they talk about the history of the Greeks. Okay, so it's a bit the situation. In Europe, there are many activities ongoing for HWO, and I cannot cover all of them. So I will try to give you just an overview and provide you the basic links. So if you are interested, you can get into that, no, and to understand the flow. So what I'm going to do is basically select a few view graphs of our colleagues in NASA on the way the US Decadal Survey has gone. And I am going to pair them with the ESA's activity. And then I will talk about the current status of the ESA's missions and planning, and the participation of the European scientists, not technologists, in HW START activities. And well, I will talk about the process that ESA is going ahead to get more involved into HWO. That included the nomination of some representatives in the science working groups like myself. And then I will conclude with some of the many ongoing European activities. So to begin with, I know that you have seen that already, but basically the National Science Foundation in their Astrophysical Decadal Survey came up with 3 key topics that relate with the worlds and sun in context. The other had to do with new messengers and new physics. And the third one had to do with cosmic ecosystem, so large scale. And then there was a recommendation that's the baseline of the HWO mission, that is NASA should embark on a program to realize a mission to search for biosignatures. Okay, so that's the key topic, and I think that my colleagues from US have already made a good and fair presentation of what is the purpose and the scientific purpose, key purposes of the mission. For those of you who are not familiarized with the history of the project, already in 2010, there were already some proposals that were related with a large UV telescope within NASA. The project was called Atlas. And then Atlas had been evolved. And finally, there were two studies that were funded by NASA. One was LUVOIR, and the other was HAVEX. LUVOIR came from Large Ultraviolet Optical Infrared Telescope. HAVEX is for to search for exoplanets. It was basically a coronagraph. And results coming up for Astro 2020 Decadal Survey was that these two should be the science made feasible by these two should converge into one mission, basically. An interesting thing from the point of view of the Europeans and the Japanese and many other countries that were involved is that in these LUVOIR and HAVEX and the other two studies, there were involved representatives of space agencies worldwide. Okay? In the case of Europe, there were in LUVOIR, that I was part of the Spanish representative in LUVOIR, okay, the representative of the Spanish Space Agency there. But there were representatives from UK Space Agency, from Germany, from Italy. There was even a representative from the European Space Agency itself. Okay, so there were also representatives from Japan and from Canada, from many countries. And so this was like a sort of a small United Nations, can you imagine? No, so there were the science and the technology and then representatives of many countries. And then for HWO, well, it was decided that at least from the European side, the representation was going to be held by the European Space Agency. So now there are not in HWO many representatives, but many of some of the people who were working on those working groups have been translated into ESA representatives in the HWO. So let's go to the second. What was ESA doing on the side? No, okay. ESA has also its long-term program, which is called Voyage 2050, and it has its own priorities. And you see that they pair quite well with NASA's priorities. One is moons of the giant solar system planets, and it's very specific in that sense. The second is the temperature of exoplanets or the galactic ecosystems. And this is very specific. It's not a generic habitable exoplanets, but it's going to the temperature because this is the kind of diagnosis that ESA mission are going to pinpoint. And then there is new physical probes of the early universe. That's the three priorities by ESA, and the time frame is 2035, 2050. So that's how it goes. As you see, there is some parent, and that's one of the reasons why, among many others, ESA is thinking and has expressed its will to participate in HW. Well, this is the representation of ESA's wheels, of NASA's wheels, and you compare this pairing, no? So exotic worlds and the search for life, our dynamic solar system, and cosmic collisions. They pair very well. Okay. How is ESA's science missions and plannings going? So for those of you who are not familiarized, ESA has 5 types of missions. It has the large missions that would be the equivalent to the NASA flagship. And basically the ongoing now are JUICE, which is an explorer of Jupiter and the lunar moons. Athena, that eventually will be launched sometime in 2035, as you see. And then LISA, that will come sometime afterwards. Athena is an large X-ray observatory, and LISA is a gravitational waves space-based detector. Then ESA has a medium class missions, and within medium class are basically there are 2 per decade. And within this medium class is where more or less the kind of budget that Europe could count on to go to an HWO collaboration. Okay. And the missions, the end missions that are approved are Solar Orbiter, which is already flying, Euclid, which is already flying, Plato, that is coming soon, and is related with the look of for exoplanets. So it's very much related with precursor science for what my colleagues were talking about HWO, and Ariel, which is even more, because Ariel is designed not only to do the monitoring, but also to study the thermal properties of these exoplanets. And from that, get more information about possible habitability, atmospheric structure, etc. Then ESA has some small missions, which are just led by other state agencies, because in Europe, we have the national agencies and the European Space Agency, to the point that once the mission is approved, the nation which leads that mission is the one that pays the most. So it's not exactly like the NASA system with a centralized funding body. And then we have the fast missions, which are missions that are for innovative implementations. Some are sort of technologically, but most of them are for science. But they need to have the technology already mature. Okay, so the F comes from fast. When the mission is approved, you expect that it flies pretty soon. And as today, we have had two. One is Comet Interceptor, which is a mission to catch up with a passing comet. And the other one is Arrakis, which is a mission to explore the background, the large scale background. Okay, well, sorry. On the right here, you have more the times. And for the time being, things are going according to the schedule. Okay? And these are the missions which are already in post operations. And as you see, there are many of them that deal with topics related not only with NASA, but with HWO. And some of them are directly shared with NASA, like James Webb or Hubble. Okay. Now, ESA has a call before this 2050 voyage, but it was issued in 2013, and it was the call for ESA Cosmic Vision. And in that call, the ESA proposed 4 themes. And the themes were planets and life, the solar system, fundamental laws, and the universe. As you see, I mean, they are more or less paired with NASA's, I think, with science, basic space science. Okay. And to that call, there was a European proposal submitted in 2013 already to build a large ultraviolet visible observatory. This proposal was called IAU, and it had some 473 scientists signing behind. Okay, so it was a large proposal with a lot of support from the community that had some clear traceability matrix, so some clear requirements. As you can see, you had there was something related or a topic related with mapping the cosmic wave and the star formation in from the intergalactic medium. And there were requirements in terms of field of view, of angular resolution. We also wanted integral field spectroscopy. The same could be tracked from stars to planets. There was another on exoplanets, and each one of them has its instrumental requirements. So that's telling you a bit of what the Europeans at that time were thinking on doing with something like an HWO. And if you feel curious about that, there is documentation. All of this is published in Experimental Astronomy in a special volume that was issued by the European Space Agency. And in the last call, in Voyage 2050, this proposal was resubmitted. And again, you can find it in a more modern volume. At that time, we identified 2 key topics that were needed. One was to enhance optical coatings, because it's well known that there is a problem with the coatings in the far UV especially. And there is a problem of having coatings that are efficient over a very broad wavelength range. So that was there. And this helped to get funding for some groups in Europe that have been working on that. Okay, Paul was talking about a group, for instance, in Spain that is working on coatings for HWO. Their funding started around that epoch because we identified that. And the same happens with the spectrographs and the design of spectrographs and design of instrumentation. And obviously with the detector performance, but both E2B at that time, it was a European company, and Fotec, that at that time was also a European company, made many developments on that sense. And in fact, E2B detectors are now the ones that are being used in all the missions. But E2B is not any longer European, it's now Teledyne's. Fotec also is not a European any longer, belongs to a US-based company, okay? And we have also a very modest, really, not really a telescope concept, but we were thinking between something very conservative, like a 4 meters monolithic mirror that can fit within the fading of an Ariane 5, and something more challenging. One was following the James Webb concept, that at the end is what is HWO is going through. At that time, James Webb was not launched yet, okay, and had been suffering many delays. So it was a sort of challenging thing to say, we are going to follow as per James Webb. And the second one was to build an off-axis elliptical mirror that could provide in not collecting surface, but could fit within the fading. And that's something that I have not heard of the HW and the NASA people talking about that. But that was an idea that was wandering around at that time. Okay. So now let's go with HW. This is a map made by NASA people with the people who is participating in the science teams in these steps. Okay. And then you have the color code, and you see that after, obviously, the US with its yellow bright, okay? The second ones is the European Union, where we have a very strong interest, and much more, for instance, than other countries which are already participating, their agencies are already participating in the HW start. These people is participating always in the science working groups, and some very few in the joint working groups. But nobody is working on the technology working groups. I have been talking about European technologies, but they are not working together. Why? Because science is ITAR-free. We are talking about galaxies, exoplanets, things like that. Joint working groups relate with the global evolution of facilities. So we have to put in there the European facilities, and there is a sort of, well, it's not ITAR nearly, okay? So, and then we have the technology working groups, which these are ITAR. So there is not interaction at technological level, at least today, between the European space technologies and NASA space technologies. Okay. Now, for the science working group, there are European astronomers all over. I was trying to dig one working group that had not at least one European astronomer, and there is at least one in all the working groups. So we are participating in absolutely every working group. And this is the distribution for European countries, okay? So the people who are the most involved in the project are France, UK, and Spain. And then followed by Germany, Austria, and Italy. Okay, that's the level of interest per countries. This is not taking into account their email, and in their email, which is the institution they are working for. So if there are many Europeans, I know at least 2 or 3 that are working for HWO, but they are working within US institutions, they are not included here. It's only the European institutions. So as you see, well, there is a very interest, and also is somewhat related also with population and relevance in ISA, so it's okay. And we also have seen this beautiful biograph that was prepared by Aki Robert. And well, I am not going to go into the instruments because these are candidate instruments, and as you have seen, NASA is already doing technological developments for all of them, okay? But here you see, I wanted to pinpoint this one, these 4 instruments, okay? And that's where the European Space Agency, or we the Europeans, are hoping to contribute, okay? And it is not defined. And what ISA has told us as representatives is that it is not the time to discuss about that. Okay, let's just go for science. Okay, and well, these 4 instruments, there are already some groups working on Europe in concepts about this possible instrument. And that is what I am going to tell you here. Okay. So what about ISA in HW? What is doing ISA? Well, the first thing ISA did was to nominate 3 representatives, Michelle, David, and myself, to attend these face-to-face meetings and all the regular meetings of the START Go map, and we follow what is going on, we inform and report. Okay. Also, if there are here any European astronomers who want further feedback, etc., well, you can just look for my name, and I am here to serve you. So is for all of you to we are there like an interface to help the community. And well, we should participate in the science, defending or representing the European interest, and we should report to ISA. And our role is within the frame of the Go map. When the Go map is finished and we enter in a phase of instrument definition, ISA probably will create a call. We don't know how. I cannot give you more details. I am not an ISA member, okay? But at some time there will be a chance to provide instruments, possible instruments for HWO. I am showing here now a bit more about which is the process, so you understand better which is the interaction of Europe in this process, because this is a NASA-based process, as has been shown in the previous talk. Okay, so the objective is to quantify the goals and to outline the instrumentation capabilities, and to build from that a traceability matrix that can be used for the design. And in the technical assessment group, let's say on the pure NASA side, they have to identify the mission architecture options, study the architecture options, and go ahead along the path that's been told. Okay, so the idea is to have everything ready to make good decisions rapidly in phase A, basically. That's what we are doing now. And the deliverables will be several reports, and those that are related with science will be distributed among the community. Those with engineering, I understand that NASA will keep for itself. Okay, so you have also seen this view graph, which is very nice because some of the technologies that are being now developed that are considered key. So of these technologies, there is one that is related with UV coatings, where Europe is working strongly, and the other has to do with coronagraphs and also spectropolarimetry, which is not here. Okay, so let's go. What is Europe ongoing? Which are the activities? This is a very plain one, because I just included few activities, and I didn't want to give you the impression that is everything in there. It's just what I am aware of. Okay, but from the point of view of instruments, for this 4th instrument that may be in, Well, there is work going on Europe on high contrast imaging, and the teams which are doing the coronagraph for the ELT, they are interested in learning about HWO. Okay. The other part is the ultraviolet polarimetry, no, spectropolarimetry. Okay. And this is, in fact, to the LUBWAR study. There was a concept contributed from Europe that was for a UV spectropolarimeter. That if you think carefully, you will realize that polarimetry requires much more energy from the source to do a fair study, because you need a much better signal to noise ratio. So having a big telescope will allow you to make an enormous breakthrough in spectropolarimetry that is not feasible with small telescopes. From the point of view of technologies, well, there is a very strong group working on multi-layer coatings to the point that even NASA is resourcing to them. Okay, so even if we European Union or we Spain are not part of these technology, these TAC groups, somewhat some of our scientists, some of our technologies are already participating on that. And then there are pros, and we have on the one hand technological pros. ECNES, the French space agency, has a very strong CubeSat program called Census. And within that, there is a probe that is being designed and with a launch in short time, which name is Castor with 2 S, not to confuse with the Castor with 1 S, Planetary mission. Okay. And this is to test the UV spectropolarimetry technology. And then from the point of view of the science proofs, and I put it on science, though we are going to test coatings and detectors, is this CubeSat led from Spain, which is a ultraviolet lunar orbiter that has as a task observe the Earth from the moon and get a view of the Earth as an exoplanet that can serve to HW test. Okay, and as you have here, the detector, this is a flight detector. We already have it. Okay, and the quantum efficiency at Lyman alpha gets about 21%. We came with those results 5 days ago. So these are fresh results, very good. And this is the ultraviolet spectropolarimeter. This is the design. This is an instrument concept that was contributed to LUBWAR by the French Space Agency. As you see, it's a big instrument. You can see there. So it's very, very big. Okay, here you have a human. Here you have a spectropolarimeter. And it is intended to do a spectropolarimetry with a resolution of average 35-40,000 in the range from 100 nanometers to 400 nanometers, basically. Okay, and there is a lot of discussion about whether to get in even more or not in terms of dispersion. And I think this is a critical view graph, because it's a plot, because it shows you that even with the loss related with doing a spectropolarimetry, this polus attached to a large habitable world collecting surface will have a sensitivity that would be about 10 times Hubble. Okay, so that's a very important things to keep in mind. So just to conclude, okay, this is a brief summary. There is a very wide interest in Europe, as you have seen, and many European scientists want to participate on that. To the point that the European astronomers are the second largest community participating in HWO. Well, the current phase of Explore the Greater Space, they can be there. And ESA science objectives and Voyage 2050 long-term program shares objectives with Son of NASA and with HWO. ISA has taken the participation to the point that has nominated representatives from the community to be part on these START activities. And well, eventually there will come up some ISA call to define ISA contribution to HWO. And as today, there are several groups in Europe working on technologies by their side. Only the multi-layers group is more or less coordinated with NASA, but it has to do because the group was in Madrid, and some of the people who is in Goddard comes from Madrid also. So there is to my knowledge, the only group that as to date is really coordinated is that, and the most of the groups are working each one by its side. And thanks a lot. This is it.
Thanks, Maria. Time for question.
Hi, thank you so much for the great talk. I have a interesting question. So when you were talking about the different working groups across the world, I noticed that there wasn't really any African countries participating or showing any interest. That sort of concerned me a little bit. So I'm trying to understand why this might be the case. Is it a lack of interest, a lack of funding, or I'm just trying to, how should we think about this? Because I would actually love to see, South Africa and just more African countries just getting more involved with, these large scientific projects. That's all I want to say.
Sorry, I have missed your question. On one side, you were asking me why there are not Europeans more involved in the technological groups. On the other one, you are asking me about the participation of South Africa in HWO.
Yes, that's just limited to, I'm just wondering why South Africa and African countries aren't participating more in the working groups. That's, I guess that's my question.
I don't know. I have not, I mean, the only figures is the ones that that was produced by our colleagues in NASA, that one here. And as you see, at that time, that was March 2024, this is open. I mean, to my knowledge, NASA has opened worldwide to any scientist. By its sound, you can sign now. If you want, you can sign now.
I'll join.
Okay, so do it. Okay, we will pass you the link and you can join in. Okay. But it's open to everybody in the planet, to my knowledge. All that has to do with science is open.
All right.
Okay.
Thanks so much.
I'll just add a comment that I had QR codes at the end of my talk that I can give you the talk at the end of when Anna's done talking, and you can sign up like right now. Yeah.
More question?
Okay.
Okay.
So time for lunch.
No
No.
question? Yes.
I have a question regarding once the observations are in place, what kind of data science is going to go on to be required? What kind of technology from the data processing perspective are going to be required?
Okay, I think that the technology for, if I have understood correctly, for the rest, he's asking about what kind of technology for data processing is ISA going to require for its participation. Okay, well, we are going to need everything. Okay, we are not going to need from this kind of artificial intelligence algorithms to massive data processing, to all kind of algorithms to optimize for features. Obviously, the data flow will be also high. So you may think of everything, yeah, that you is, and I don't know how it will proceed, but I bet that not only ISA, but also NASA is going to need all sorts of activities on that sense. No? Artificial intelligence is going to play a key role on this. Kevin wants to add something.
Yeah, I wanted to ask something. Oh, there is an artificial intelligence and machine learning working group that you can also sign up for. You can see when I give the other QR codes. But so Anna, when we met in 2022, not long after the Hab Worlds was announced, there was discussion about ESA contributing something like an M-class mission at the M-class mission level to an instrument for Hab Worlds. Is that still the thinking? Or what is the long-term goal investment level that ESA is interested in?
Okay, I am not ESA.
But you are the representative.
Okay, the only thing I know about that is that nobody has told me that this is not going on. So what was said at the time has changed.
One more last question.
It's not a question. So Kevin, I'm actually a member of the SVC. I'm in fact the head of the Dutch delegation. So I'm also not ESA, but I can say that there is very active interest at the national level, at the ESA level, about a significant contribution to habitable worlds. The exact scale of that contribution is still, of course, under discussion. I think you say the M class or sort of $500 million. That's certainly been discussed, and even larger potential contributions. So it hasn't been nailed down yet. It's not a money in the bank, but there is that level of interest from the European community is absolutely present to contribute to this mission.
Okay, before moving to lunch, I would like to invite you to the two scientific sessions that we will have in the afternoon about polarimetry, a lot of things, but also the contribution from Africa and South Africa, mostly, but not only in the radio field. So we will have important talks in this field. And last but not least, we have also more than 80 posters, and most of them are very interesting. So I invite you during the time to give a look. So thanks again to the speaker, and see you in the afternoon.
Hey guys, shall we get started? We can take your seats. If there's anyone out there, you can just ask them to come in. So thank you very much for coming to the session. We don't want to keep you here very long, and we know that there's lots of things going on in this meeting, and but one of the main things. So just to run through what's going to happen today. I'll just open up with some words, and then we'll hand over to our Southern African regional office, who wanted to use this occasion to celebrate their 10th anniversary. Our other offices have also celebrated anniversaries, but this one happened to coincide. It was the 14th of August, if I'm not mistaken. Was it 14th of August, 2000?
start. This will be a lot of interesting science, very different. Very interesting instrumentation. So we will start with Mr. Steve Darst, who will tell us about the International Lunar Observatory. Okay, so please. You have a microphone over there? Okay.
Thank you, Dr. Gomez. Good afternoon. Thank you very much, Dr. Gomez, for making this session and presentation possible. My name is Steve Durst. I'm the director of the International Lunar Observatory Association based in Hawaii. So I extend my aloha and greetings. Hawaii is actually, if you dig the proverbial hole into the ground, into the middle of the earth, you come up in Hawaii. We're antipodal, both hemispherically and globally. So a long way. But not as far as to the moon and this adventure that we've had. So with this presentation, I'll give you an update on the status of our project, our observatories. Talk a little bit about the instrumentation you can see on the upper right. The center two images there are on the moon actually already, having functioned somewhat to standards, but not up to all of our plans. The top right instrument, we'll talk a little bit more about the projected first American-Chinese moon mission selected for one of the 6 international payloads selected for Chang'e 7 in 2026. The image in the center is our flagship, long sought mission to the mountain on the moon, Malapert Mountain, which for us is the ideal place to operate for both observation and communications. And we are trying our utmost at this moment with both NASA, the Chinese Space Agency, and other space agencies, as well as private sources, to stage a mission to the South Pole Mountain on the moon that I'll have more to talk about in a moment. Okay, we can, do I have a slide projector here? I guess I do. ILOA, its purpose, like many observatories and astronomical undertakings, is to expand human understanding of the cosmos through observation from the moon. Our organization formed out of the pursuit of that idea for many years. And in fact, astronomy from the moon, we'll look at the history in a moment, goes back to the beginning of the Apollo era in the 1960s, because it seemed like such a logical thing to do. We were formed after, so say, 15 or 20 years of pursuing this idea as a nonprofit, IOC, in Hawaii, with the main functions of, like any pioneering venture, you have to be able to conduct a number of tasks, field a number of positions. The two that we chose most fundamental are observation and communication, since ILOA is closely affiliated with a publishing company, Space Age Publishing Company. We intend to publish broadcasts from the moon after we conduct observations, and to participate in what drove many of us interested in space and lunar exploration in the projected build-out on the moon, humanity becoming a multi-world civilization, which we were for a few fleeting days in the 1960s and 70s. We worked and lived on 2 worlds. Some of those are still with us, some of those moonwalkers, Buzz Aldrin and others. So we intend to participate in the human development, the human settlement on the moon. And as I just commented to Dr. Gomez, we don't go to the moon just to do astronomy, but when we go to the moon, as we're doing now, not just well, the international community. Looking up astronomy will be one of the first things that's done. I'm fairly sure, a first light industry, so to speak. So, the questions why are obviously a self-evident question, and there's some fairly straightforward answers. The far side of the moon has long been an obvious location to do astronomy, radio astronomy, since it's radio free, one of the few places in the solar system that has that asset of having the Earth itself be a shield from radio transmissions from Earth. There are quite a few advanced efforts now to preserve a radio-free environment in some manner on the far side of the moon. It's certainly going to be a challenge, but for all of us, it's important that these assets be preserved. So, why is astronomy from the moon as a shield or radio quietness platform? Very stable platform, capable of VLBI interferometry. The exosphere, the atmosphere, extremely thin, as we all know, thinner actually than LEO, than low Earth orbit, the atmosphere on the moon, exosphere. And finally, the servicing, the axis, while at this point, space observatories, which are more than half a century old now, have been leading the way on off-Earth astronomy and observation during this time. Astronomy from the moon will be easier to maintain and service once the settlements, once human activities commence. So accessing the instrumentation is a great advantage. One advantage that is not listed here that also should be is at 1/6 gravity. All kinds of different manufacturing techniques and technologies will be possible. You know, I've always wondered about refractors reaching their peak at the beginning of the 20th century because of the force of gravity. They got to be about a meter, and then gravity distorted the optics. With 1/6 gravity on the moon, I don't know what the future for larger refractors could be, but 100-meter telescopes, radio antenna, and other facilities are certainly feasible and larger. And again, any place on the moon, all one needs to do is look up. One can't do every kind of astronomical technique using every wavelength from every place, but every place on the moon is able to support astronomical investigation, and we will see, I believe, global placement of observatories and telescopes like we do on Earth. Wherever there's civilizations and people wanting to explore and look out, there are observatories. So the whole sky, the whole universe will be open to continuous high-resolution observation. Our intent is to do galaxy imaging first and other astronomical observations, but again, anything in the cosmos from the new frontier of astronomy that the moon will be is a legitimate new pursuit of knowledge. Brief history, because the actual conduct of astronomy from the moon has required getting there, which is obviously the big challenge. But I mentioned the 1960s. There were studies done out of University of California on the advantages of astronomy from the moon. Arguably the most accomplished astronaut of the 20th century, John Young, who was on our board of directors. He made 7 missions into space, including one from the moon. And he did place the first telescope you see on the lower left, the far UV spectrograph, developed at the Naval Observatory, and that sits. You can see that in the image where the astronaut John Young is to the right of the flag, and that highlighted squared image in back is that instrument still there, gold anodized. That was one of the more well-known images that was taken by that camera was the photo of the Earth's geosphere, coronosphere in UV on the center of the image. Fast forward to 41 years, the first landing since the 1970s was conducted by China on Chang'e 3, late 2013. We had a number of MOUs with China going way back. So we're able to collaborate with the Lunar Ultraviolet Telescope, about 15 centimeters, that rode atop of the Chang'e 3 lander landed about 41 degrees north on the moon, and working with astronomers at the University of Hawaii in Hilo, Dr. Pierre Martin in particular, we were able to successfully image the first spiral galaxy, the first galaxy spiral from the moon, M101, and the control image from an Earth-based observatory is to the right to validate that M101 finding. So those are the only two, with the one exception of Chang'e 4 has had VLF dipoles operating on the far side of the moon for about 4 or 5 years with a limited success, some dipole technology issues. But other than that, so before I get to continue the story and tell you about the new telescopes that are on the moon, want to divert to our flagship mission, as I mentioned in my introduction. A antenna to conduct first light imaging of the Milky Way galaxy center, transmit the data to Earth, as many of the 8.1 billion people as we can, and then conduct other astronomical observations with the idea that, and there have been efforts now to get that first image of the Milky Way galaxy ever from the moon, that it could have, if explained and publicized properly, could have the same, similar impact in consciousness raising about our future, that when we went to the moon in the last century and looked back at Earth, and that image resulted in great changes and understandings, the entire environmental ecological movement. So when we go back, as we've gone back in the 21st century, the Chinese lander was not able to image the Milky Way galaxy, nor did our mission in February, this last February, succeed in that. So it's still to be accomplished. So ILO1, which will have observation and communications functions, is aiming for that mountain on the moon. The image on the left is an actual photograph from the Japan Kaguya orbiter in 2007. Why that mountain on the moon? Why is it valuable for us? Because it gives 24/7 line of sight to Earth for observation and communication, both critical functions that we are pursuing, observation and communications. The peak, the so-called peak of eternal light, it's not eternal, euphemistically named, but the peaks at the poles do receive the oblique sunlight up to 95% of the time. So you solve the great extremes in thermal challenges by operating on the peak on these mountaintops that get 90% of the time of power sunlight, close enough to the now sought after pole traps harboring likely ice water. Well, they do have ice water. We don't know exact quantities or how to make use of it. Other advantages from the moon's south pole are the vast Aitken Basin, the largest impact basin in the solar system, about 2,500 kilometers in width. It's a treasure trove for geologists as well as mining interests that may need to be addressed. The southern skies, including the Milky Way, are target rich for astronomers. Antarctica, we've explored the seventh continent on our world, so it's somewhat analogous to explore the south pole of what is increasingly called the eighth continent of the moon. I missed one. That's another image of the South Pole area that NASA's and China and India and Japan and Europe and private companies are looking at seriously because of the ice water assets there. Malapert you can see in the center foreground, and to the right in the foreground is Malapert A, where our ILOX instruments that we'll talk about in a moment touch down and are presently located. And if I can go back one. So we've talked about some aspects of our landing site, of our preferred mountain on the moon landing site. Here's our ILOX by persistence and a little bit of good luck. We were on the Intuitive Machines Odysseus lander in February 22. It touched down, the first landing on the moon from the USA this century, in fact, in over 50 years. The first independent commercial lander, we were on that, the first to that Malapert Mountain area. So that's ILOX, and we have a little bit of imagery. I don't know how many of you followed that mission. After 3 or 4 independent landing missions crashed, including one from Israel and one from India in 2019 and one from Japan in 2023, and another one from US, Astrobotic, a few weeks earlier, before ours had a propulsion failure just after launch. So we were on the Intuitive Machines 1 Nova C Odysseus. It 27 months late, but it launched successfully by SpaceX, took 4 or 5 days to get to the moon, conducted in-orbit final preparations, and there was one landing software component that wasn't properly installed. They had to improvise, Intuitive Machines, and the lander didn't crash, but they think while it was landing a little bit too fast, one of the 6 landing legs caught a crater and tipped over very gently. And our instruments were not mobile, so we didn't get too much from the landing. They're still there, though. Let's go back a slide. Those are the instruments aboard the IM-1 and 2 Intuitive Machines Odysseus lander in the clean room in Houston before shipping to Florida. You can see them circled, riding on the top of the craft. ILOX was named Kaimi by the Hawaii students in a competition. Kaimi, well named, it means the search or the searcher in Hawaii. That's a narrow field of view. And on the right was a wide field of view that was named Lunar Codex by an auction we had, a naming rights auction. So that's a tall spacecraft. Some people think that the height was a factor in its unstable landing. It's over 4 meters. Those were our goals, as I mentioned, Milky Way galaxy imaging. And we invited a dozen astronomical observations from distinguished astronomers and observatories around the world to participate, and extended that invitation to our future ILO-1 mission. So we're going forward with new missions. The goals of ILX, I mentioned astronomical Earth observation and the local lunar environment. Those are ideal goals for ILO1 more Earth, long duration observation of Earth and the local lunar surroundings. Hardware validation of functionality and survivability and communications. We sent quite a few digital files for various uses that we are using now. And here's the incoming image from our wide field camera, image of you can see the Earth up there at about 11 o'clock from the bright sun. You see the crescent Earth. So that's a picture of moon, Earth, and sun with our wide field imager. And the sequence, there's taken from the spacecraft there, the landing legs of the spacecraft incoming a few minutes before touchdown. So that imagery was taken with our camera, and that's the lunar surface as well. That crater on the top left is 9 kilometers in diameter. To give you an idea of size, that well-preserved crater on the left. One in the center is not named, we believe. And then finally, we touched down on the moon. The spacecraft was tipped over. So our narrow field of view just got fuzz. Our wide field got that image. Didn't expect to get that glaring image of the sun, but I guess that's heliophysics 101, our first image from the moon. You can see because it was the wide field was a fisheye lens, you could see the parts of the spacecraft. Well, the spacecraft that we took that image from is on the left of that image. And on the bottom at about 7 o'clock, you'll see a little streak, which we believe is one of the landing legs of the Odysseus spacecraft that snapped off upon skimming before touchdown. Another similar picture there. We did get some star trails with the narrow field of view. You can see Taurus there and the Pleiades, which are special to Hawaii and many cultures like Japan and Italy. And there's with the lines drawn in the Pleiades and the lower right and Taurus. That's what we were expecting. That's what we were expecting with the cameras that were built by Canadensis, a company in Ontario. And that's what we hope to achieve in the future. As I mentioned, that was an MOU signing with Hong Kong University Space Lab personnel on the left and NAOC China personnel, myself on the right. As I mentioned, our proposal for Chang'e 7 was accepted. We've had some questions about who exactly is going to build the camera, but that's due to be launched in 2026. The Shackleton Rim, which along with Malapert Mountain that I mentioned, is our second choice of landing. There's a good chance that NASA's Artemis 3, carrying the first woman, first international traveler, will land at Shackleton Rim. And that's where ILOC, China's planning to land robotically there in 2026. We'll see if NASA Artemis plans to land there as well. And future moon missions, we're sponsoring our ILOA has conducted Galaxy Forum programs since 2008, over 100 such programs featuring any science educational aspect in the galaxy. We're holding a major one in Hainan, China's Hawaii, as it's nicknamed, in December, with the theme Astronomy from the Moon and human moon mission landings, and also solar system complete. We're beginning to study, now that we're approaching the first quarter of the 21st century, 2025, we can get a handle, I think, and make some fair projections of what we can do with the next 75 years. And I really hope all the astronomy organizations and space agencies in the world, think tanks, universities, do take a visionary look, not just at the next 5-10 years, but we're a quarter away through the 21st century. So this Galaxy Forum Hainan will have the theme solar system complete in the 21st century. And I'll end with how I began. Aloha, and thank you for your attention.
Thanks a lot for this talk, this beautiful talk, and the perseverance behind it.
Yeah.
Okay, so anybody wait a moment, anybody has any question for Steve? No? Yeah.
A couple of curiosities. First, from the data that you got after landing, did you get any information about the dust on the moon after landing? I mean, with your camera, did you get any data that could be useful?
Well, if we go back and see that image, we're looking at a lot of dust. So
yeah, but I mean the behavior of the dust.
That was actually there were other experiments on board that mission. There were 5 NASA experiments and 5 independent ones. I think NASA had one other astronomy mission called ROLSIS out of the University of Colorado, which wasn't imaging the dust per se as much as the photoelectric environment above the lunar surface. So that would be a place that I would go to, and I'd be happy to introduce you to Jack Burns, the PI. That might answer have some data on that for you. That wasn't our direct mission, but there were instruments aboard that got data that related to that.
If I may go for a second curiosity, I'm surprised that U.S. instrumentation could fly on Chinese mission. So I was wondering whether you have any limitation in that.
Well, at this point, not so much. In fact, collaboration seems to be increasing. I think with the Chang'e 5 returned moon samples that NASA has given permission for U.S. scientists to use, Chang'e 6 from the far side also. And we're astronomers who tend to get a pass. Scientists do. We've been working with China for 30 or 40 years, so that's nothing new. And we also are very affiliated with, as I say, a publishing company, and that would be a good story. So we're pretty much left alone.
Okay, thanks a lot. Yeah. Go.
Thanks very much for the nice talk. But could you maybe explain a bit about how this association formed and how membership works?
Yeah, that's a good question. The organization formed through the pursuit of that idea through our publishing company and at conferences with colleagues from about 1990. And we held a series of meetings in 2003, 2005, and ultimately 2007 in Hawaii with interested people, and thus formed the association. We do have a status a little bit unclarified on ILOA associates, and that will be made amplified and made more explicit later this year. Right now, ILOA consists of 28 very distinguished directors around the world. 3 astronauts. I mentioned John Young was our emeritus astronaut, and I think half of the directors are astronomers, PhD astronomers, business people, educators, enthusiasts, and a small executive committee in Hawaii of 4 or 5 of us. And in between, we are forming this associate status. So
That is one and last question.
It's called Space Age Publishing Company. We publish a weekly called Space Calendar, which tries to tell what's going to happen next week. We've been doing that for 40-something years without fail, and that's what we intend to broadcast from the moon. So thank you for that question.
Okay, so thanks again. Thanks a lot, Steve. And our next speaker is Juan Soler, and he will talk about polarization. So,
okay, good afternoon, everybody. See if my slides arrive. It's already a tough act to follow, no? A telescope on the moon. How much cooler can I get? So hopefully I'll get you to get enthusiastic about polarization. So I received the non-negligible task of reviewing polarimetry across the electromagnetic spectrum. And of course, I have my bias. So if you don't like them, we have others. So we can check. Okay, so this is going to be heavy on the radio and near infrared review, but I hope I have something for everyone. Okay, so why do we care about polarization to begin with? Is because the light. Hi, Marco. This is the director of my institute. Now you see him. So the light that brings us the information from space is polarized. Part of it is polarized to some or other degree. So in a way, polarization is a way to get more information from every astronomical observation. It's just not very easy. So the easy thing to do is ignore it, but that doesn't mean it's not important. So let's check what I'm going to talk about. I'm going to give you a very brief polarization primer, such that you know what I'm talking about when I say linear polarization, circular polarization, and stuff. And then I'm going to introduce you to this very quick ride through astronomical polarization from radio waves. Okay, so polarization is a property of electromagnetic waves. So it's a way to characterize light as much as the wavelength is. So it comes in different flavors. And in particular, polarization is the way the electric field vector behaves in an electromagnetic wave. So if you project the electric field vector on the plane perpendicular to the direction of displacement, it can form a line. That's what we call linear polarization. If the electric field vector is just going up and down with respect to that projection, we call it linear polarization. It can be circular, it can be tracing a circle, it can be moving around, or you can have a mixture of the two, and that's what we call elliptical polarization. This is measured with this formalism. I don't have many equations, but this is called the Stokes-Muller formalism. Chandrasekhar introduced that into physics after the work of Gabriel Stokes was lost for almost half of a century. And so if they ask you in a cocktail, what do you need to learn about polarization? That is described with three numbers, the Stokes parameters Q, U, and V. If you don't care about circular polarization, you can ignore the V, and then you just stay with Q and U. That Q and U describe the orientation of that electric field projected in the plane perpendicular to the direction of displacement in a funny way. Because, for example, Q gives you the orientation in two orthogonal directions, and U gives you the direction in two orthogonal directions at 45 degrees from the initial one, okay? Very few people can see in Q and U. You'll see astronomers that tell you, yeah, you can see this result in this Q and U map. It is very hard. It takes years to train for this. Because what we actually measure is two things. One, the orientation angle. So how is that electric field vector oriented with respect to a particular line in the sky? So, for example, if you do use galactic coordinates, it's with respect to the north galactic pole. And the polarization fraction, which is the amount of polarized emission that you have. Okay, so you just divide it by the intensity. Actually, this equation is upside down. Sorry. Okay, so polarization every day. We use polarization every single day, basically because every phenomenon of interaction of the light generates polarization. The most simple of them is polarization by reflection. Every time you have an incident ray of light that is unpolarized and is reflected off a surface, it acquires a polarization which is parallel to the direction of that surface. Another way in which we use polarization every day, we have filters. Most of the optical equipment that we have filters that constrain the direction of displacement of that electric field to just one line. And when we put those two together, we have something like that. When you look into the surface of a lake, you'll see some of that reflection. This is the sky reflected on a lake, okay, or on a pond or whatever you want. When you put on your glasses with a polarizer, you're able to see something that you were not seeing before. The light gets polarized when it bounces off the surface, and then you put your polarized glasses, you get rid of those reflections. That is a very basic optical system. And of course, if you want to do it more complicated, there's a formalism for that. It's called the Muller matrices. So why is polarization complicated? Because every single optical element in your telescope and between you and the source is inducing a polarization. So in the end, what you're trying to solve is an inversion problem. You're trying to put many matrices, one after the other, for each of the optical instruments in the path of your telescope, but also in nature. That's why polarization is so hard and it's difficult, because it's a problem of matrices and inversion of matrices, and that is very hard. Okay? So let's get ready to polarization across the electromagnetic spectrum. So we're going to start by number of photons. So we're going to start with the high wavelengths or low frequencies. Okay. In the radio, I chose to cut here with the atmospheric cutoff for radio waves. And let's start with polarization. Most of the polarization that we see in radio waves comes from the synchrotron emission. So the synchrotron emission is produced when you have charged particles that get trapped in a magnetic field. That induces a rotation motion by the Lorentz force, and you generate a polarization in the light that is emitted by those electrons that is parallel to the magnetic field. The amplitude of the polarization signal, or the polarization fraction, depends on the velocity of those incoming particles and on the strength of the magnetic field. So you can also get images from that. So basically, what you see when you look at synchrotron emission or polarization in the radio is you're seeing magnetic fields very far away that are trapping the local plasma. What do we do with that? Well, first we see a very different universe. This is a portion of the galactic plane observed at 1.4 gigahertz. So this is the CGPS. The SGPS is a galactic plane survey made with a radio telescope in Australia. And this is intensity of the light. So this is unpolarized, and this is the polarized light. Okay, you can still distinguish some of the point sources. These are other galaxies. These are active galactic nuclei behind our own Milky Way. But you see, in polarization, you see a whole bunch of structure. Most of that structure is in an own galaxy. That is the plasma that is surrounded and is mixed in the different phases of the ISM. You're seeing electrons, you're seeing magnetic fields there from everything that is between us and those galaxies that you see here in the background. And you see it's very different. For example, here, these bright points, those are supernova remnants. You don't see them so well in polarization, but you have more emission there. So what have people discovered out of the 20 years or so that we have known about these things? That these features are very hard to interpret, basically because we don't know exactly what they are, but they have something in common, and some of them are very elongated. So we see these depolarization or polarization canals. And that is interesting because they might be produced by the plasma interaction with the light that is coming from the rest of the galaxy. And that is produced by something that we call Faraday rotation. So what is Faraday rotation? It's an effect of polarized light. When it crosses through a magnetized medium, it acquires a phase. So that angle of polarization changes depending on the electron density and the magnetic field in that intervening medium. So that we call the rotation measurement. So you measure it with an fit. You measure polarization at different wavelengths, and then you make a fit. If you assume that there's only one source along the line of sight, if you have something in the background, then you call that Faraday depth. Okay? And that Faraday depth has an expression that is depending on the electron density, the magnetic field, directly pointing towards you, and the path length. Okay? That is what we call Faraday density, Faraday depth. This Faraday depth is very complicated to interpret, but people have devised very, very smart ways of dealing with that. And the most famous of them is called Faraday synthesis. So if you imagine that what you measure is a function of the polarization angle and the wavelength, you can apply something like a Fourier transform. Don't say that it's a Fourier transform. People that work in the radio get really mad because there's like the beam of the telescope and there's the fact that you're only assuming one source. So it's not a Fourier transform, but it's a Fourier transform. Okay? So don't say it out loud too much. And why is it interesting to do that? Because let's say you have your telescope here and you have 1, 2, and 3 pieces of intervening ISM. And then you measure your Faraday polarization, your polarization at different wavelengths. If you apply the Faraday synthesis, the result is this thing that you have down here. You have components that correspond to the different pieces of the ISM that are between you and that source. So it's a way, the Faraday synthesis is a way to decompose the contributions of different portions of the interstellar medium into the observed signal that we have. And that is very cool, because if you can divide the ISM into different contributions, you're learning a lot about the structure of our galaxy. If you don't care about our galaxy, but about other galaxies, you learn about the foregrounds that hinder the observations of more distant objects. So this is cool. It's cool, but it's not easy. So let's look at it. The people that have advanced a lot with this are working on low frequencies, on megahertz, hundreds of megahertz frequencies. And there, the leaders are probably at the LOFAR observatory that measures between 10 and 240 megahertz. Why not at the higher frequencies? Remember that there's a dependence on the wavelength squared. So at higher frequencies, you can see further because you get less rotated, but the effect is less evident. So at lower frequencies, you see more Faraday rotation. So this is one of the most surprising results. This is by Vibor Jelic, that was interpreting a field that was supposed to be devoted for cosmology. Vibor was looking at a piece of the sky at high galactic latitude where they assumed that maybe there was nothing interesting there. You see, this is a field that is a cosmological field. It's LIS N1. It is a cosmological field where they observe lots of background galaxies. Then Vibor came to Paris while we were working in Planck, and he showed these images. And he was interpreting these as stellar streaks. He was saying these most likely are stars that are crossing along the line of sight and are producing a path of ionization. The problem is you need a very powerful star to do that, and you need a very powerful star that is moving, and you also need to find the star that is producing those things, those scratches down here. So that was not the right interpretation, but it was the right place to show these things, because there were many ISM scientists that pay attention to this thing that used to be just a foreground to cosmological experiments. So now we have things like this ones. This is the work of Anna Ersek, and this is the Faraday synthesis of a big portion of the sky. This is in galactic coordinates. So this is a band of the sky like this. So if you want to see it at night, and you do your arms like this, and then you can do this all the way. This is almost 90 degrees if you do it like that. This is a big portion of the sky. And there you see many Faraday components. You see some that are kind of related to the galactic structure most likely, but at high galactic latitude, you see very weird things. You see things like these ones. And I'm not going to pretend that we know what this is. But this is the structure of the plasma close to our local bubble. This is the structure of the ionized medium around our local bubble. So you can see some of the background structures, but you can see that it's not regular at all. So we have been playing with what does this thing know about other tracers of the ISM, trying to disentangle the structure of these things, like what are we looking at? And this is the work of Andrea Bracco, who compared 21 centimeter observations with these streaks, and it turns out that they match. The neutral hydrogen emission know about the orientation of these structures. Also, the polarized emission from which we infer the orientation of the magnetic field. These are structures that are not in the ionized medium. This is at the boundary between the ionized medium and the neutral medium that we sample with the 21 centimeters. So we are seeing here structures in the multi-phase ISM, and I think that's the take-home messages. We're seeing coupling between ISM phases. What else are we learning for? Well, stay tuned, because more things like this are coming. At higher frequencies, you can also look at the whole sky. So this is the result of the NVSS Faraday rotation experiment. This is around 1.4 gigahertz. So you're looking a little bit further, simply because you're not Faraday rotating that much, so you're losing less information. And then you're looking basically at the magnetic field of the galaxy orientation. So blue is going away from you, red is pointing towards you, modulo the electron density that you would have to model. This map was made with those almost 40,000 sources, but now there's a way of regularizing those maps. So the current models of the magnetic field of the galaxy are based on this kind of regularized data. Of course, it's very hard, because you saw how difficult it is. We don't have distances to these things. These appear as some rotation and velocity channels. So it's always difficult to have a full interpretation for this. And as we see the magnetic field of the galaxy, what we expect is the largest scale magnetic field. We also see some very small scale features. So we're always very happy when we have something that we can really link to some of the structure there. And that's what happened in 2019, when we were looking at Faraday rotation towards the galactic plane, and we found an overdensity of high Faraday rotation in this region of the sky. Here you're seeing at Faraday rotation for extragalactic sources, so stuff that is behind our galaxy. So we're seeing the Faraday rotation. The crosses are pulsars within our galaxy, and the boxes are dispersion measurements, so places where we know the electron density. And we combine all of that data to show that there's an overdensity in Faraday rotation. There's a very high Faraday rotation, almost 4,000 radians per square meter. That's a big number. It's the biggest one that has been measured. And it happens to be towards the tangent point of the Sagittarius arm of the Milky Way. So we think we're seeing the squeezed magnetic field, and we can marginalize it from the electron density because we have this dispersion measurement. So we think we're seeing the magnetic field that is being compressed by the passage of the spiral arm. And we have modeled that in galaxies. Of course, this is not the Milky Way. It doesn't have a bar. The arms are not the arms. But in these simulations, we can infer that more or less the order of magnitude of the effect is that one. We see enhancement wherever you have this passage. So at least we have one object for which we know it is the structure of the Milky Way that is producing the enhancement in Faraday rotation. Okay, let's go to the next wavelength. And why is it interesting this? Because the future is going in this direction. So with the advent of new interferometric arrays, we're going to have more and more observations. Of course, at the higher frequencies, like the new generation BLA and the DSA 2000, they both are amply shown in this meeting. And of course, the square kilometer array. So the square kilometer array is very interesting because it's happening now. One of the objectives of the SKA is the origin and evolution of cosmic magnetism. And the precursors of the SKA are already yielding some results in magnetization of the galaxy and of the universe. So one of them is this MIghty polarization survey. This is done with Meerkat. This is local. You can ask them more at the stand of SKO, but they are looking at the magnetization in cosmic filaments. They're looking at very dense fields where they have observed galaxies, and they're looking for the magnetization in and around those galaxies. Same with POSSUM, which is a much larger survey. This is the POSSUM pilot field. These are supernova remnants, but they are going to enhance the density of sources for which we have Faraday rotation. Right now, as we speak, we have around 1 Faraday rotation source per square degree in the sky. We're going to have a factor of 25 by the end of POSSUM. That means that we can sample much better not only the ionized medium in our own Milky Way, but we can separate the components that come from our own galaxy, from the intergalactic medium. So we're going to have estimates of magnetic fields, not only in our own Milky Way, but in the medium that is separating galaxies further than ours. Okay, 7 splitting, or Equilafis, I'm not going to talk about that. I'm almost out of time, so ask me about it later. Microwave. Why is microwave very important for polarization? If you make a census of the energy in photons in the whole universe, microwave wins. So as most of the photons in the universe are in the form of CMB, of course, CMB polarization is very important. So this is just the universe SED. This is the cosmic microwave background, cosmic infrared background. So the CMB, of course, is very important, but it's also a way of looking at the infancy of our universe. The CMB acquires its polarization, which is linear polarization, through the Thomson scattering of the electrons at the surface of last scattering. So this is the place where the CMB gets released. And that scattering produces a linear polarization. That linear polarization looks like this, which is hard to interpret, and they apply another way of separating polarization. So remember I told you about Q and U? That is a local basis for inferring polarization. You can also do a non-local way of separating polarization in what they call E modes and B modes. They always put this, as if I was not part of that community, we always put this as if people could just calculate the Fourier transform and the combination of Q and U that you need to separate this. So it's really hard, but I guess the cartoon is there's some modes that are like gradients and some others that are like rotationals. That is the E and B modes. And why do we care about that separation of polarization like that? Is because in the E and the B modes of the CMB polarization, we have the information about primordial gravitational waves from the inflationary period of the universe. And that is extremely important because it explains why our universe is like we see it now. Solves the homogeneity problem, the anisotropy problem, many problems. And also it tells you about the optical depth at the epoch of reionization. Tells you what was the optical depth when the universe was producing the first stars. And that is very cool. So it looks like that. cosmologists use this multiple decomposition. So what you're seeing in the x-axis is different scales in the sky. So the whole sky is around here, multiple L1, and at smaller scales, you go in this direction. So this is the power spectrum that we all should learn, because it's the basis of our Big Bang cosmology, of lambda CDM cosmology. Then here are the E modes, and here are the B modes. The B modes have a contribution from the galaxies in the intervening universe and a primordial component. So that is very good. That is what they want to measure. They want to measure the amplitude of those B modes, and the amplitude of those primordial gravitational waves is comprised in that R parameter. That's why cosmologists that work in CMB polarization always want to measure R. What is the problem? R is buried under foregrounds. We're seeing it through our own galaxy. In particular, we're seeing dust and we're seeing synchrotron. So I already told you what synchrotron is. So we're going to talk about dust polarization. So on the low frequencies, you're dominated by synchrotron, and on the high frequencies, you're dominated by dust. That is the game of modern CMB science. Try to disentangle the contributions from those foregrounds into the signal that they measure. This is the most up-to-date estimation for R. And there are many telescopes that are following this path from the ground. There is in particular the Simmons Observatory that is going to increase by 2 orders of magnitude the number of detectors. So they're really going to drill a hole in the sky in sensitivity, looking for signal from R. To look at the other foreground, the dust, you need to go to higher higher wavelengths, to higher frequencies. Sorry, to higher frequencies. So what do you see there? So we have high frequency observations in the near infrared of the whole sky. The most common of them is from the Planck instrument. And what you see there is this. So this is one of the most iconic images in astronomy, not because I was part of the team that produced it. This is the orientation of the magnetic field projected on the plane of the sky and integrated along the line of sight. Here, that Van Gogh kind of pattern is the product of aligned dust grains along the line of sight. So what we're seeing is in the background, there's a starlight that is unpolarized, heats up dust grains there, and the emission from those dust grains is polarized in the direction perpendicular to the magnetic field. This is a very fast evolving field in the sense that on the year when I was born, there was one polarization vector in the far infrared. There was one. 2 years later, there were 2. With Planck, we have tens of thousands of vectors towards the same region that they observe at much lower resolution. So we have lots of information about the magnetic field, and that's allowed us to study the coupling between the magnetic field and the matter. Dust polarization in the far infrared tells us about the magnetic field in and around star-forming regions and about how the magnetic field regulates the processes of star formation. Of course, there was life after Planck, so we flew a balloon, blast ball, that we used to observe polarization in different frequencies, and we solved a mystery. The observations of polarization from the ground were showing this B-shaped pattern, but these were observations from the ground where you have to point at very bright targets and you cannot cover very large scales. This was a puzzle for the people modeling dust. So when we observed it with blast ball that had different capabilities to Planck, we could see that it was actually flat. So it matches better our models of dust. So don't worry, we don't understand dust, but we don't understand it. It's not as bad as we thought it was when we had this V-shaped polarization that is produced by radiative transfer effects and different populations of dust. Okay, so we had Sophia, and Sophia brought us a very nice vision in 4 different wavelengths of nearby star-forming regions. We learned about the structure of the dust. We learned about magnetic fields in other galaxies, and then it was canceled. But we always would have CMB. So right now, from balloons, we have access to these 280 and 350 gigahertz bands that hopefully are going to give us some more information about the magnetic field at resolutions that Planck didn't reach. So Planck was limited. And of course, we have new polarimeters like this one, the Taurus mission that has been proposed. Is the only polarimeter outside of the atmosphere that has been approved, but there's other missions that are coming along. Of course, there was a Spica, and it was rejected. So we don't have any far infrared polarimeter to follow up with these studies. And we really need them because from the ground, it takes 10 to the 5 times longer to do the same science that you can do from space. So here is the ground. here is us. So we really need a far infrared polarimeter out there. Okay, you can of course do interferometry and go for smaller sources. That's what the people are doing with ALMA. And now let's move into the mid-infrared. People are measuring the mid-infrared. The same dust grains that are polarized, they're measuring them in very small fields of view. So they're really bisecting star-forming regions at much higher resolution. In the near-infrared, there's mostly not private initiatives, but like person-motivated initiatives. That's the one from Dan Clemens that produced this beautiful instrument. It's called MIR. It's a near-infrared polarimeter that he used to sample the magnetic field through the galaxy. So when you look at Planck, you're really seeing all of the dust emission. You're seeing all of the line of sight and also with a relatively large beam. Planck resolution is 4 arc minutes. With MIR, what you're seeing is the individual stars for which now we have distances and at much higher resolution. So we can see that the magnetic field of the galaxy is not as boring as it may seem. It's actually composed of many vertical structures, and it has been pulled and thrown around. So there's lots to learn about the structure of the magnetic field in our own galaxy from these observations. And of course, it's also useful for planet studies, because the light from the debris dust, from the debris disk that is around young stars in which we think planets are formed, that light, by scattering, is polarized, while the central star is not. So polarization is very important to disentangle the disk from the central star, and that is the reason why the corometer in the coronagraph in the Roman Space Telescope includes polarization. So let's go into the visible. The visible keeps growing, but most of the information in the visible comes actually now from Gaia, because we know where those stars that we have been using to sample the magnetic field are. So people are now advancing a lot in the field of magnetic tomography, dividing those stars in different density, in distance bins, and tracing the magnetic field in structures that are nearby and are not confused by the background. So like in this case, this is the Radcliffe wave. And there are surveys that are being planned to include more and more observations. Now let's go to the high energy, which is easier because there's less observations. There are 28 observations of polarization in the ultraviolet. As you go into higher and higher energy, you have to really squeeze your photons. Each is more complicated. So these are 2 missions, one that flew in the space shuttle and one in the international, in the HAST. We only have 28 lines of sight. And why do we want more? Because you learn a lot about stellar feedback and the properties of the radiation of early stars, and particularly about the dust. And if there's an astronomer that tells you that doesn't care about dust, you know that he cares about dust. Dust is very important. The reason why we care about dust in the ultraviolet is this is the Sierkowski curve. This is a way in which you can use polarization to infer the properties of dust grains. So the peak tells you more or less the size of dust grains. So you can use it kind of to sample the sizes of different dust grains in different environments of the ISM. Since we don't have points on this side, we really don't know how are the small grains aligned and what is the distribution of sizes of dust grains. And that is very interesting. Then we have the future. This is a MIDEX polarimeter that has been proposed. Something like a WMAP for polarization. It was included in the decadal survey, is not approved yet. So hopefully, yes. In X-rays, for a really long time, before 2021, there was only one observation of polarization in X-rays. And it came from this also 8 satellite. It was the Crab Nebula. And all of that has changed thanks to one mission. And this mission is IXPE. It's a satellite that has been measuring polarization in X-rays in a systematic way. So you can learn more about why is this important, why is it important for example, the spin of black hole, for very high energetic phenomena inside of our own galaxy in Division D. Actually, this afternoon after the session, I'm not telling that you should go to the session, you just have to split yourself in 2 or maybe see the video later. There are people that are working on modeling the source of these highly energetic events. And polarization is extremely valuable because if you cannot advance with more photons, you can really squeeze more information out of each photon that you're measuring. So IXPE, and one of my favorite results from IXPE is this one. This is a polarization measured towards an object that is close to the galactic center, and these are ripples in the radio emission. If you go downstairs to the SKA stand, and then you see this beautiful image of the galactic center, those filaments, those are those filaments. And they're finding that this outflow is actually perpendicular to one of those filaments. So of course, we don't have the statistics to sample if there's actually a coupling between the strong magnetic field that is producing these parallel structures and the magnetic field that is producing this wind nebula that is polarized. But this is very cool because now we can start to ask those questions that we couldn't before. There's more in X-rays. And finally, in my last minute, there is, of course, gamma rays. And in gamma rays, there was only one observation, and there's still one observation that has been made towards the same object. It was made with integral towards the Crab Nebula. And of course, we come back to the beginning, polarization fraction, polarization angle. And now has been repeated by this Indian satellite with a different polarization angle. And of course, you can learn about the physics of these compact sources, gamma ray bursts, active galactic nuclei, magnetars, pulsars, and many others. So what have we learned so far? Polarization is hard, but it gives you lots of information that you wouldn't know otherwise. It gives you a new vision of the sky. At the low wavelengths, at the long wavelengths and low frequencies, we're learning about the ionized medium and the multi-phase structure for ISM in our galaxy and in the intergalactic medium. So that's very interesting. That in the far infrared is more complicated, basically because you have to observe it from outside of the Earth's atmosphere, and we don't have a projected mission. In X-rays, we have a very good prospect with XPE and with other proposed missions to observe in the ultraviolet. And there's a great amount of discovery to be made by connecting the different phenomena that are related to anisotropy, and in the end is the cause of polarization. So just because polarization is complex doesn't mean that it's unimportant and that is boring. Thank you.
It has been a real review of all this. So, any questions in the audience? Not, no questions? No? Then I have many. Let's go, yes, but one simple one. When you are detecting all these filaments in radio frequency, do you think that there could be phenomena similar to what is observed in the sun that produce an ambipolar filamentation of the matter in the intergalactic environment or on the galactic halo? What part is of what?
Yes. So that was one of the first ideas that we had. So, of course, the ionization is not enough to have something similar to what we see in the solar corona. These filaments are very elongated and then in polarization have the same pattern. But modeling of the skin of the neutral medium structures is where we're going at. So it's the same principle. And of course, these structures may be periodical because they're also strongly magnetized. So in that sense, they're analogous to solar corona, but the ionization conditions are very different.
Yes.
So it's much softer, but I think it's related, yeah.
Okay, thanks a lot. Any further question? Then let's thank our speaker. And now we have to go to our next speaker, who is Yossi Svartbar, and who should be speaking online. Is he online?
Yes, can you hear me? Can you hear me well?
Yes.
Can you see my screen?
No yet.
So I am sharing it.
Okay, let's see. Can we? Now we are seeing it.
Okay, great. Thank you for the organizer for allowing me to introduce Ultrasat, although remotely, and sorry for that. Ultrasat is a wide field UV space telescope led by the Israeli Space Agency and Weizmann Institute, where I come from. And it is in a collaboration with NASA and DAISY from Germany. This is a completely different mission than spoken until now, and this is to study the transient universe. And as I think many of you know, transient astronomy and time domain astronomy is taking a center stage in our current studies. And this is interesting for many reasons. First of all, as astronomers, we are interested in the sources themselves, right? To understand our stars are merging and colliding and exploding at the end of their lives, maybe disrupted by massive black holes. But moreover, these transient events allow us to study more fundamental questions about our universe. For example, how LV elements are formed and how black holes are formed and how the environment is impacted by these supermassive black holes. Now, although these questions are with us for centuries, only now we can systematically study them. And this is almost as always thanks to development in technology. We need wide field surveys in order to capture these transient astronomy, and we actually have these in many, many wavelengths, as you can see. In addition, more recently, we have what we call multi-messenger astronomy. So not just getting light, but also gravitational waves and neutrinos. But what is missing in this framework is UV. And Ultrasat is exactly trying to fulfill this gap. Ultrasat uniqueness is in the first step is in its wide field of view. And this is really wide field of view. We're talking about 200 square degrees. Its high sensitivity is in the near UV, so 230 to 290 nanometers. And it will be located at geo orbit, and later I'll explain how it is and why it is so important for transient astronomy. So on the plot, what you can see is a comparison between various transient surveys, and y-axis gives you the grasp or the accessible universe volume in arbitrary units where Ultrasat is one. And you can see that Ultrasat is about 300 times better than Galaxy in terms of studying transient phenomena. And if you're going to compare it to current ground-based surveys, which is the big bulk on the middle, it is about an order of magnitude or a bit more better than that. It will be comparable to LSST Rubin, which will be the next the next talk after me. However, it will give us a different window in terms of wavelengths and also in terms of cadence. So Ultrasat will have some of its field observed in a minute time scale continuously for months. So we can study the phenomena of transient events at very different time scales. And it will also produce real-time alerts that will be publicly available to the community to also follow these events that we will detect in all other wavelengths, and including also, of course, in spectroscopy. In addition, Ultrasat will have the ability to respond to incoming alerts. Maybe we are mainly focusing on GW events, as I will see later, and we can slew to any place on the sky where the sun and or Earth do not intervene. So this is, at the worst case, 50% of the sky within 15 minutes from receiving a trigger, and then observing there for at least 3 hours in the worst case. So Ultrasat was designed with two main key science goals in hand. The first is, as I described, responding to GW alerts by the GW detectors, and to search for the EM counterparts. And this is very important, for binary neutron star and neutron star black holes. We can study, again, a lot about the physics of these events by getting this electromagnetic counterpart. Now, starting 05 in 2027, maybe 2028, we expect to have several tens of binary neutron star mergers per year with an arrow box of about 100 square degrees, which is a very good fit to the Ultrasat field of view, because within one or maybe 2 pointings, if it's an elongated region, we can cover the entire GW arrow box. And we can localize very well the source, first to tell the entire community where is it so everyone can follow it, but in addition to observe it in the UV and to have UV light curves. And as we learned from the only currently EM counterpart of a binary neutron star merger, it is very bright in UV and it has very important information. In addition to that, in most of the time, we're going to do a blind survey, searching for all sort of transit events and mainly supernovae. And we're going to detect hundreds of supernovae per year. And the large sample is actually important to also discover the rare events, only by having several types of supernovae and measuring their properties, we can try to understand and map the relation between progenitors and supernovae types, and with that to understand the physics of this phenomena. Now, having such a big step forward compared to the current surveys, we will not only address these two key science goals. We actually have 13 science working groups working on different fields, and here is a list. Again, 2 lines out of this is what I described until now, but we are talking about science from solar system science of comets and asteroids through exoplanets, stars, and of course going to extragalactic studies, also AGNs and TDAs. We expect to have thousands of these kind of events. Switching to the implementation of Ultrasat. So Ultrasat is, as I said, is an Israeli-led mission. The spacecraft will be built by the Israeli aerospace industry. It will carry a single payload, the UV telescope that will be built by ELOP with a 33 centimeter clear aperture. The contribution of our German collaborator DESI is the focal plane array, or the camera, as we call it, that will have the UV sensitive sensors built by Tower. We will be launched by 2 GTO by NASA, and our current expected launch is at the end of 2027. In terms of reliability, our instrument will be reliable for at least 3.5 years of science mission. In terms of fuel, we will have enough propellant for 6 years before we need to evacuate to the graveyard. You can see here some information about the dimension and power. And the mass, you can see most of the mass of Ultrasat is actually in propellant that will be required transferring from the GTO to our geo orbit. Now, we passed all design reviews and specifically the critical design review almost 2 years ago or a year and a half ago, and we are already into the production phase. You can see some pictures of actual hardware. So on the top is the camera, top left, the camera structure and sensors. These are development models, but we are already building now the flight models, and we expect it to be integrated, tested, and sent for integration with the telescope at the end of 2025. We already have in hand all optical elements, and the assembly of the telescope will start later this year. In terms of the spacecraft, we got the propulsion system only 2 or 3 months ago, and we are actually now expecting the structure to arrive to Israel to start the integration of the entire spacecraft. So I'll try to detail a bit about the technological aspects of these parts. The first is about the spacecraft. As I said, we are launching to GTO, and we have to have self-propulsion to go from GTO to geostationary orbit. This will be done via a set of maneuvers at the beginning of the mission, and then we can stay there for 3 or 6 years. The geo orbit is very crucial for our science. This allows us from a single ground station to have continuous communication, both for real-time download of the data as well as real-time slewing of Ultrasat if we get interesting incoming alert. It is far enough to allow us to have a large covering of the sky. So at the worst case, where we are between Earth and Sun, we still have 50% of the sky. And also in terms of background noise, this is better than, for example, a LEO orbit. The camera is composed of 4 BSI backside illuminated CMOS devices. It is built by DESI. We achieve a very high quantum efficiency, almost 80% at peak, and average within our waveband of 60%. Through a custom ERA coating, we actually tested several ERA coatings and selected the one that is optimal to our wavelength. And with that, and after cooling to 200 Kelvin, we have a very low dark current, very low read noise. As I said, the flight sensors are already been produced, diced and tested, and they are now being ranked for selection of the flight sensors. And we have several papers out describing the development of the camera. In terms of optical design, we have a unique optical design led by Dr. Sagi Ben-Ami here in our department that is trying to maximize the grasp, so maximizing the accessible volume. So what you can see on the left is our color dependent and position dependent within the field of view PSF. So on the y-axis is the radial distance, and on the x-axis the wavelength. We are focusing on the near UV, but actually our best PSF is not at the center of the field of view, but at a circle at around 4 or 5 degrees off axis. This allows us to have a larger grasp. This means, as you can see on the plot on the right, that we have an effective PSF which is source dependent and position dependent. So for our typical explosions where you can estimate them as like a very hot black body or 20,000 Kelvin, and or a G-dwarf, we will have a mean PSF of about 8.5 square degree, 8.5 arc seconds, sorry, throughout the field of view, while for red sources, our PSF will be much worse. Now, translating it into limiting magnitude after taking into account also the noise, this means that we'll have also a source and position dependent limiting magnitude with a mean limiting magnitude of 22.5 per visit. And a visit, I'm talking about 3 consecutive images of 300 seconds. So for a 900 second integration, we reach to 22.5 for these hot sources. What you can see on the right that actually our dominant background noise is not instrumental. It is first it is zodiacal light. Second is actually Cherenkov radiation, which are due to energetic particles hitting the external lens in our Schmidt design, and only then dark current read noise, electric noise starts to kick in. Now, we also can reach to almost millimag or a bit better than that at the bright end. Again, we are mainly focusing on the faint sources and not bright sources, but still for bright sources, we can actually achieve also interesting information, for example, for exoplanetary studies. Now, while 22.5 is our limiting magnitude per visit, we will have, for most of the extragalactic field, hundreds, and in some areas even thousands of images. So we can actually co-add them and build a very deep image of the extragalactic sky until we're going to reach the confusion limit. So also the confusion limit is position dependent, but roughly we expect to get to between 24 and 25 AB magnitude at the deepest end. Now, to answering the key science goals that we were aiming for, we actually have 3 modes of operation, but the first 2 are trying to answer these. So first, we're going to have a survey mode that we're going to devote 21 hours a day for one field of 200 square degrees and imaging it every 5 minutes. So we can study phenomena at very short time scale, at a minute time scale, for example, shock breakout from supernova. In addition, we have a locate and survey covering 40 fields, all of these extragalactic fields, with a 4-day cadence. So, this is at the complementary 3 hours per day. And with that, we can study phenomena which is more slowly evolving, for example, TDEs. Now, for both of these modes, we are going to have real-time data download analysis, and 15 minutes from the end of the exposure, we will send to the entire community public alerts on transient events. In addition, at every given moment, we can have a target of, sorry?
You are running out of time, Yossi.
Okay, I'm gonna minute with 1 minute, 1 or 2 minutes, please. In terms of target of opportunity, we can, as I said, slew within 15 minutes to 50% of the sky. We actually have no hard limits on the number of TOs except of those with negative power balance. And wherever we're going to point, we're still going to have continuous communication to the ground, so we can also analyze and alert to the community on the localization. And at the beginning of the mission, we're going to devote about 3 hours per day to build a UV all-sky map, which will first be a very deep image, deeper than the current state of the art, but also important as a reference for the target of opportunity. So let me conclude with this slide. So I told you about ULSAT. This is a wide-field Israeli-led space telescope. We're gonna try to have an impact on transient astronomy, but actually we can have an impact on a much broader science cases with a wide-field UV space telescope. And all of this with a relatively small and affordable satellite that also a country like Israel can lead. And I will end with that. Thank you.
Thank you, Yossi. So there is time for just one question. Is there any question in the audience? Yeah?
Hi, Yossi. Thank you for a very nice talk. Can you say a few words about your data releases? Are you going to make eventually your catalogs available to the whole world, or how will it work?
Yes, thank you. This is a good question. So in terms of data policy, first of all, as I said, the alerts will be public immediately with some basic information about position and a few points. In addition, we're going to have a 12 months proprietary period, and after which we're going to have public data releases happening every 6 months. So this will be open to the entire community, and of course, within our collaboration, the collaboration members have access to the entire images.
Okay. So let's thank Yossi again.
Thank you.
And let's go for the last talk of this session, which is about the Roman telescope. And well, I hope that you remain here. We are a bit late on the schedule, but I think that the talk is going to be extremely interesting. Thanks a lot, Dr. Ivesek.
Thank you. Are you sure you want to stay? If you want to leave, I won't be offended. First time, second time? No? Okay. So I have 2 slides that talk about time domain with Ruben, but in order to explain those 2 slides, I will give you a few slides of introduction to Ruben. I will tell you briefly about where we stand with construction. We believe we will start LSST survey next year, and then I'll conclude with those couple of slides with more technical detailed information about what to expect in time domain from LSST photometry and astrometry. The unique thing about Ruben is not so much its large mirror. There are telescopes that will have much larger mirrors, but its unique thing is a very large field of view that enables it to scan the sky 100 times faster than any other 8 to 10 meter telescope. Here is a comparison with other US public telescope, Gemini South, that is our neighbor in Chile, and its field of view is in the upper right. Ruben field of view is lower right, 100 times larger, 3.5 degrees across 10 square degrees. For this reason, we can deliver legacy survey of space and time in 10 years instead of 1,000 years that it would take with Gemini South or North. In those 10 years, LSST will deliver about half of the sky observed 1,000 times in these band passes. So it's very similar to SDSS. The main difference is that SDSS Z band was split into 2 bands that we call Z and Y band in order to improve sensitivity to high redshift quasars and other objects, to push it to about 7 for Z dropout objects. There will be no time allocation committee. It will be survey mode where cost-benefit function is optimized by so-called scheduler, essentially AI, running the telescope. You can see here this black dot jumping around that's 1,000 times faster than in real life. It will take 40 seconds for each observation, 30-second exposure with readout slew roughly 40 seconds. There will be about 1,000 observations per night. It will take 3 to 4 nights to cover the observable sky, and we'll do so for 10 years, eventually having 1,000 observations for each point on the sky. Comparison of the data itself, this is teeny tiny region on the sky, 1/10 of moon's diameter. This is down to 22nd 0.5 magnitude from SDSS in GRI color image. If you go 5 magnitudes deeper or 100 times in flux, you will get something like this. This is a real image. This is from Subaru telescope, which can of course go to 27th magnitude. It cannot go over the whole sky as fast as Rubin. But this is very illustrative of push in quality for astronomical surveying that we will get from Rubin. Whenever I get low in motivation, I go to these 2 slides and go back and forth to make myself motivated. It's not about data only. We will also have exquisite software pipelines that will produce products that will be science ready, products that you will be using to do your science. So all the things, all the steps that everyone would have to do, like calibrating images in astrometry and photometry, finding objects, measuring their properties, all that will be done for you, and you will be able to access data through our Rubin Science platform. It will be loaded once per year with static data releases, but for time domain science, you will get information about what changed on the sky within 60 seconds from closing the shutter in Chile. Data will flow from Chile to California, where every new image will be subtracted from co-edit images obtained prior to that point, and all the objects in different images, like in this example in the middle row, all the objects that appear in different images will be measured and reported to a web stream called Alert Stream that you will then be able to follow up. You will be able to filter it any way you want, and then follow up those objects for more photometry, for spectroscopy, for polarimetry, for whatever is needed for your science. So let me now just spend a few minutes tell you where we are. The top row is computer-generated design for the observatory, for the telescope, and for the camera. The bottom row are actual photographs of the existing hardware, which shows that, yeah, it looks like it was designed and it's even operational. This should run. We did have some problem with setup. This is telescope. Okay, let's skip this one. This is the camera. It is the largest astronomical camera ever produced. It's 3,200 megapixels in focal plane with 189 16K CCDs. On the right, those small squares, they are 16 megapixel CCDs. There are 189 of them. We can read this camera in 2 seconds, 2.4 seconds to be precise. And the reason is that there are 16 segments on each CCD with 16 amplifiers. And so we can read the whole focal plane so fast. That's because we want to maintain very high efficiency of observing. Our standard exposure time is 30 seconds. The camera had its own problems, but they are all fixed by now. And this is photograph from May of this year. This is at the summit in our observatory. Camera arrived in May. Now it's in clean room. We are repeating tests like the one shown on the right-hand side to establish that nothing was damaged during the transport. It will go on telescope in December. We expect first images of the sky with this camera in January or February. However, we are just about to put commissioning camera on the telescope in about a month. Commissioning camera looks just like this one from the outside, but from inside it has only 9 CCDs, not 189. But we will use it for a few months to practice with adaptive optics system and to debug software to do other commissioning steps before we put the big camera on. So these are roughly the dates. We should be done with construction by next summer, at which point Rubin Observatory becomes a unit of NOIR Lab, NSF's NOIR Lab, the main US National Observatory, and LSST should start in late 25, calendar year 25, and then after 1 year of data, there will be first data release. There will be lots of data. So how are you going to get to data? This will be the main tool, Rubin Science Platform. In many ways, it's similar to what other surveys produced. It is more exquisite because there will be more tools. You will not have to download data. You will upload your software. I will just, in the interest of time, talk about notebooks, show a few examples. You can already access all of this to learn how to use it. All those links on the left, they are exquisite Python notebooks that demonstrate how to use our science platform in order to do analysis of light curves, to look at the proper motions, to look at images, etc. There is exquisite documentation by our already existing operations team that can bring you and your students up to speed to be ready to do science with Rubin starting in a year from now or so. Here is an example of a little bit of Python that produces something that is like color magnitude diagram, more or less. You don't have to download it. This is all done in our computer center. You only download like plot or whatever you want to publish, for example. You can look at images. You can do all kinds of things. In the context of time domain science, you may have your favorite object. You give its array and decan. You ask, give me all the data that Rubin produced up to tonight, and then you can analyze and continue doing that. So how big is this data set going to be? It will be the largest photometric and astrometric time domain data set ever produced in the history of astronomy. Not just the largest, but it will be larger than all the data we collected collectively since the beginning of astronomy. And so much data, of course, requires different tools. That's why I just showed you these Rubin Science Platform tools. So it's time to start learning with your students how to use that. There will be in the catalog, static catalog, about 40 billion objects, but about 20 billion stars and 20 billion galaxies. Not all of these objects will be detected in every observation in single visit depth. There will be, we estimate, between 5 and 10 billion objects that will have light curves with about 1,000 data points. Photometric light curves, and of course, astrometric data, time domain data that will be used for measuring proper motions. And just to give you an idea about precision and accuracy, this is comparison of astrometry and photometry coming from Gaia and from Rubin. So Gaia is in red lines. Gaia, of course, is space-based survey, and at bright end, it can achieve precision that there is no way to be matched from the ground. But it doesn't go as deep as LSST will go. And it is a coincidence. It looks like intelligent design, but it's essentially coincidence that at the overlap magnitude of about 20, the precision and accuracy of Gaia and LSST are comparable, are similar. So from the astronomical point of view, if you just don't pay attention which mission is which, from the astronomical point of view, it looks like a grand design where we go from 12th magnitude to 25th magnitude with time domain, and we have fantastic photometry that is now sub 1%, and we have astrometry that at the bright end with LSST will be as good as 5 to 10 milli arc seconds. At the faint end of LSST, it will still be as good as 0.1 arc second or so at the 24th magnitude. So it is truly transformational, both in precision, in accuracy, in the number of objects, in the length of baseline, and in the size of data, including the tools to play with it. It is truly a new era for astronomy. And given we have coffee, I will skip the remainder of my talk, and I'll stop here to leave time for a few questions.
Thanks a lot for a very nice talk and for your understanding. So, any questions from the audience? No? Okay.
Thank you. Is there going to be alerts for variable stars, the new ones, based on the light curve?
So we will alert on everything we detect in difference images within a signal to noise above 5. And then if we match that object astrometrically to previously detected objects in our database, we will tell you about it. Like it's not new thing. We already have, we'll give you even 30 days of past history of observations in alert packet. We will also update ephemerides for solar system objects, and we will compute where they should be known solar system objects. And then if it's matched to solar system object, will tell you this object in alert stream is most likely solar system object. So you don't follow it up as, for example, gamma ray afterglow or whatever would be more interesting than just a plain asteroid.
If I may just follow up, how do you manage variability versus transient?
We don't. We tell you about every detection of an object. If it was previously observed in that direction on the sky, there will be information about it in alert packets. We'll tell you, oh, this is not first time we detect something in that position. We actually have like 10 observations. Here they are. If it is the first time we detected this object, then it may be something super interesting, or it could be faint variable star that just became brighter than our threshold. It could be junk. There will be lots of junk too. We will have 2 observations per night that are designed to capture the motion of solar system objects. So if you were to look for something really, really exotic, like some afterglow from gamma ray bursts, then you would actually wait for the second observation and you would say, I never ever before detected anything in that position. And now 30 minutes apart, I detected it twice. It can't be junk. It can't be just some boring variable star. It's better be something really interesting. Let's do follow up and see what we see.
Questions? I have a question.
There's one there behind you.
Okay.
Okay, thank you so much. My name is Hanoku, and thanks for the great talk. And my question is about, is there an automated method for finding and showing the previous observations of the alerts?
To assure that previous observations, I didn't catch last 2 words in your question. I understood everything except the last 2 words.
I mean, a previous detection of alerts.
Yes. So when you get new alert,
yes,
there will be information about previous detections. There will be also linked, not the first year, but after that, there will be linked to the same object in our previous data release,
yes,
where you can then do much more exquisite analysis if you want to. So basically, the system is designed that we tell you everything that we know based on our data up to that point.
Yes, I understand. Thank you.
Okay, now my question related with mathematics and informatics students that want to use this amazing data set to play with algorithm. How would that be feasible? Would that be to use this to train our students on new algorithms for massive data mining, etc., etc.? They should have to use the Jupyter notebook, or they can do it in a more efficient manner?
Yeah, absolutely. Absolutely. There is a lot already done in this context. I teach my own students with this approach. There are a number of summer schools that were held where all the materials are public. There are also books about this that either from astronomy or outside of astronomy. It's very relatively easy to get students up to speed. And then, of course, with this Rubin Science platform, when we have real data loaded in, they will be able to try different algorithms, different approaches. So it is actually excellent playing ground for anyone, any student interested in machine learning, artificial intelligence, cutting-edge statistical algorithms, even if they are not interested in astronomy per se, but they want to learn machine learning on something interesting. What's better than astronomy?
Thanks a lot. Let's thank our speaker again.
Thank you.
And we will be back in 15 minutes, I guess.
Thank you very much. So first of all, I need to acknowledge my two co-authors of this paper, George Nicholson, and those of you know George. George is the history of radio astronomy in South Africa. He epitomizes it. And Pancho Maruping, who is the MD of SORAO and is very much part of the future of radio astronomy in South Africa. And then I'm the sandwich in between. So just to preface this, it's a history of people and places punctuated with telescopes, and there's going to be absolutely no science because Roger's going to talk about that afterwards. It's also a history of South Africans in radio astronomy, which is subtly different from the above, and also some space science I'm going to throw in as well. Being South Africa, it's a history that bears the imprint of colonial and apartheid oppression. You can't avoid that. It includes institutions and individuals who are complicit in this oppression. And at this stage, I have to acknowledge my own white male privilege in South Africa. That's given me opportunities that I would not have had if I hadn't been of this skin color and of this gender, at the expense of a lot of other South Africans, and I have to acknowledge that. It's an incomplete and probably bad history as well, with author bias, unfortunately, but and it's not going to be chronological. Can't do that really with these sorts of talks. It's more thematic, and I'm going to be talking about my own university, about Hartbeespoort, very briefly on the SK and Meerkat, and Roger's going to be talking about the Meerkat's achievements after this, but also because it's more recent history and people know about it and it's being written about, and human capital development. And so I'm going to focus on the early days, things that people perhaps don't know about, but also how we got to where we are. People often think, well, how did South Africa end up in this situation? And there was a reason for it. So a bit of geography first off. South Africa, we're here in Cape Town, the home of SORAO, SKAO offices here as well, SAAO, UC, and the universities, Stellenbosch, University of the Western Cape, and UCT. Up in Gauteng area, there's Hartbeespoort, obviously, Wits, University of Pretoria, Northwest University, which is actually in Northwest, not Gauteng, but it's up that end of the country, and the University of Johannesburg. These are all players that we're going to be speaking about. My own town, Rhodes University, well, my own university, Rhodes University in what was Grahamstown, now Makanda, the site in the middle of the Karoo. UKZN in Durban, UFS, the University of Free State, and the Boyden Observatory. SALT and SAO, and of course HES up in Namibia. So that's the geographical landscape. And even though the talk says 65 years, I'm going to go back before radio even and talk about somebody called Selmar Shonland. He left Oxford in 1889 to come to Grahamstown, now Makanda, to run the herbarium at Albany Museum. In 1896, his son, Basil Shonland, was born. Selmar Shonland, the father, founded the South African Association for the Advancement of Science, the so-called S2A3, and he facilitated the formation of Rhodes University by extorting £50,000 from the Rhodes Trust. Rhodes was dead at this stage, and his trust had some money, and that's why we got the name. But his son Basil is really the important one. He matriculated from St Andrews College in 1910, which is in Grahamstown, age 14, got a BSc from Rhodes University College. World War I, he got involved in radio already, signal services of the Royal Engineers, and then went to Keys and Cavendish Lab to continue his studies after the war. Returned to South Africa, did some research into lightning, then World War II came along, and he got involved in radar development, along with Lovell and all of the others, and was a superintendent of the Army Operational Research Group. So he was in the UK, and then in 1945, the then Prime Minister of South Africa, we had Prime Ministers back then, Jan Smuts, recalled him to South Africa to form the Council for Scientific and Industrial Research, the CSIR. He was the first Chancellor of Rhodes, and then he ended his career in Harwell in the UK. So Sir Basil became OMG, CBE, FRS. If you're wondering what OMG is, it's not, oh my God, it's the Order of Mapungubwe, which is is the highest civil order in South Africa. He got it obviously posthumously. I fortunately came across this on the internet, a random newsletter from my own university, 1959, September. And it was an article on the physics department at Rhodes. It says that in 1929, the department outgrew itself, and we got a new building that Rutherford opened. And in 1938, it produced three remarkable graduates. Two of them we're going to speak about here. Frank Hewitt. Now, whenever you see a yellow highlight, it's a person you have to remember because they're going to be coming up later in the story. And Jack Gledhill. Jack Leadhill was professor of physics at Rhodes, and in fact, he was professor of physics when I joined Rhodes. And there he is giving me the S2A3 bronze medal for my thesis back in 1983. I had hair then. Then this is we go on to more people. Pat O'Brien. George Nicholson gave a very good talk on Pat O'Brien at the Meerkat at 5 conference. So in this newsletter, it said that in 1945, Pat O'Brien was the first physics student to write a research thesis, a research MSc thesis, which would be the standard going on from there. He then went to Cambridge, and he worked with the great and the good in Cambridge, with Graham Smith, with John Baldwin, and others, and wrote some really fundamental papers about the force at the center of the galaxy and also about the sun. And then he came back to South Africa and he went to Durban University of Natal, Durban as it was then. And he got involved in ionosphere works, working with Des Clarence on whistlers and things in the atmosphere. So he was the first radio astronomer, first South African radio astronomer. Nobody knows really about too much, but he was really very fundamental in getting things going. Then there was this guy, Zach Forsyth, who I found no information about. I can't find any living person who can tell me about Zach Forsyth. But he got to know about radio astronomy when he was at Durban from Pat O'Brien. And he clearly knew about electronics, and clearly knew about radio astronomy. And he started what's said here, a thriving research group into solar radio noise with various people. And so he instituted the first radio telescope in South Africa in 1958, the year I was born. This was the first MSc project that came out of this telescope by somebody called W.L.H. Shooter, who people don't realize is a South African, because Bill Shooter then went on to Jodrell Bank to start off with, and then he went over to Canada and started radio astronomy at University of British Columbia, and used the Penticton telescope to map out the northern hemisphere. Spoke to Russ Taylor earlier. Didn't realize that Bill Shooter was a South African. So the very first real South African radio astronomer. Just to give some more geographical context, this is Makanda, Grahamstown, and I've pointed out some things on here. You can see where the first telescope site is up there. Shonden's is memorialized with his father in the botany department down here. The Albany Museum was where the older Shonden used to work. And we'll go on to the 22 gigahertz telescope but shortly. But very importantly, the Rat and Parrot, local pub, which gave the name to the Rhodes research group, RAT, headed by Oleg Smirnov these days. So there was the shack. And it had these low-frequency telescopes built with vacuum tubes. The bottom right picture over here is I took last week. That's where the site was. So the shack was basically over there, but the campus has changed a lot since then. And these were the graduates that came out of the shack. So Pat Wild, who went to work with Rod Davies at Jodrell, came back to UCT as an astronomer. Graham Poole went to Sheffield and got involved in meteor physics, and then came back to South Africa. His advisor was Tom Kaiser there. Gerard Fiscure went on also to Rod Davies as a supervisor at Jodrell Bank, and went on to NRAO and all sorts of other places thereafter. Lots of people don't realize that Gerard, co-editor of Galactic and Extragalactic Radio Astronomy, was a South African, and Gerard de Jager. So Gerard didn't actually do radio astronomy at Rhodes. He did ionospheric physics under Gledhill, but he also went and then worked with John Meeban and basically built the spectrometer for the Jodrell Bank back in the day. Gerard then came back to South Africa, first to Rhodes and then to University of Cape Town. Then there was the Jupiter years. Jack Gledhill was Professor. Eddie Bart come back to Rhodes. He was a student at Rhodes. He was a nuclear physicist out of Liverpool. And then there was a whole lot of stuff going on about Jupiter, because Gledhill was interested in magnetospheres and ionospheres. He then got interested in the magnetosphere of Jupiter and predicted that Jupiter would have an oblate magnetosphere because of the rotation. And so there was a growing interest in Jupiter. And so the next thing was to build a Jupiter observatory. The sites were chosen away from the campus for RFI reasons. So first at Jamison Dam, and two students, George Gruber and Hill, did MScs and PhDs that came out of that. And This was an old R206 World War II radio receiver, a real bomb-proof thing. And you can see that it was, back then, the CSIR that Shonland had formed was funding the research that was being done. Just another picture showing the greater Grahamstown area, because now, we had to move out of town because of RFI. And so there was the Jamison Dam site, and then they had to move to the Craig Doon site, which is in a valley to get rid of out of the RFI. And then there's the two Vinex sites, which even today one is the site for the TART radio telescope. And you may have seen one of the TART telescopes downstairs in the exhibition center. I tried to operate a Horn telescope from there once upon a time. And the very first interferometer in South Africa was operated from Vinex. And we'll see a bit more about that later as well. So down in Craig Doon, a whole lot of these antennas were built. There's a whole antenna farm, and the person here with the yellow background is Dirk Baker. This was Dirk's MSc. If you read it, it's a real tome, basically built radio telescope end to end, including the antennas. Got to learn about antennas, got to love antennas, wrote up his MSc, and John Krause got hold of him and said, "You must come and work for me at Ohio State University." And he went across and he worked with Krause. And he wrote a PhD, focal region fields of parabolic reflector antennas of arbitrary F/D ratios. Clearly very important for radio astronomy. So there was Dirk, very important, got the yellow background over there. Oh, the other thing, there was still RFI here, and he worked out that it was coming from the power lines in end-fire mode. And he worked that all out analytically, which was then confirmed later when we were establishing the Meerkat site using numerical codes, which showed that that was in fact correct, that's the way things work. Now, when you go into history, you've got to find the history, you've got to get your base data. And so in our department, we have the big black book, which was really the handwritten records of all the students. And so somewhere between cuneiform and Excel. And if you look in there, you'll find in 1964, Peter Harvey. Peter Harvey did honors at Rhodes, and then he went on to Jodrell Bank, and he built the first of what became Merlin. He built a single baseline interferometer between the Mark II and then Mark III in Wales. So another South African radio astronomer that people perhaps didn't realize. Peter then came back to South Africa. Mike Ings, he built the first antenna interferometer in South Africa. He got an honors degree in 1973. We just need to slip in here. He he did his PhD in London and then came back to UCT and various other things. But an important player was what's to come. At Rhodes, we then moved on to a 22 gigahertz telescope, actually moving now into the microwaves. And a number of students were involved in this project. And most importantly, in our context here, Mike Gaylord, but Graham Obram as well, were important. And this is now getting into the transistor era and computers to do things. So now we step to the north, to near Johannesburg. And there's some sites that we need to look at here. Hartbeespoort, obviously, very important, mostly for the Heart Radio Telescope, but also the mini-track station, the satellite tracking station, and the Telkom site. So there's a whole bunch of antennas out there. Estlin Park is where a lot of it all started. You'll see that just now. And then the Republic Observatory in Johannesburg, where things happened at the NITR that developed. We'll see that coming up now. And of course, importantly, Wits University as well. So Frank Hewitt comes back to us now. So he was, born in Grahamstown, attended St Andrews, just like Shonland. And also in World War II, he was involved in radar with Basil Shonland. At the end of the war, Shonland said, "Come back, I'll need you at the CSIR." And he's to work on lightning studies, and he carried on. He got his PhD in the lightning studies. But he was a great internationalist, and he got NASA involved and said, NASA said we needed a place to put a mini-track station, and that was put up at Estlin Park, which we saw just now. He then went on to become the director of the National Institute of Telecommunications Research, and was instrumental in getting NASA to put up a tracking station at Hartbeespoort. He ended up as being a VP of CSIR. He also got SAAO going in South Africa as well as a joint venture with the UK. This is an important point. Hewitt disagreed with Shonland. Shonland said we should not have radio astronomy in South Africa. He'd worked with all the radio astronomers, or people who became radio astronomers. He said, Australia were too far ahead and this was going to cost too much. But Hewitt didn't agree with him. So he disagreed with his boss, which was a good thing. So DSIF, later DSS 51, was built at Hartbeeshoek. And basically, Hewitt had undermined Schonland because there were these opportunistic things that happened. Rhodes University had shown that you could build cheap radio telescopes, and you could have opportunistic use of things like these DSS stations. So enter George. George worked at the mini-track station at Esalen Park and then moved on to Hartbeeshoek when that was established as a servo engineer. NASA had a host nation program, so you could do radio astronomy on NASA equipment. And Pat O'Brien, remember him from earlier, suggested that, look, there's this 25-meter telescope in the Northern Hemisphere at Alvaro. They've done a Northern Hemisphere survey at 960 megahertz, do the equivalent for the Southern Hemisphere. George did that. And he wrote that up. And this is a picture of George, which I only found a couple of days ago. I don't think anybody, even George, would recognize himself there. But basically, using the NASA equipment. George then worked with Australian colleagues in the Deep Space Network to do VLBI. This is the very, very first VLBI to be done in the Southern Hemisphere, between Joburg and Woomera, and then between Woomera and Goldstone. And so this was very, very fundamental stuff that was being done. And George had always been interested in the variability of quasars. He was now able to get some sort of imaging, spatial information on them as well, and wrote up his PhD. George told me this 2 days ago. The very first fringes made with the Effelsberg 100-meter telescope between Hartbeeshoek and Effelsberg. Anybody know that? Never published. But NASA's days were numbered. There was political pressure, certainly from Black Caucus in the USA, that they should disinvest from South Africa. And this, in fact, then did happen. And it was an unexpected, the announcement was very unexpected. And so it was reported in the newspaper. And this is how people found out. But Hewitt had been approached by a journalist and was asked, what are you going to do? He said, about what? He said, well, NASA leaving. He says, we're going to carry on doing radio astronomy. Unfortunately, I could not find that copy of the newspaper. It's the one issue in the archive that isn't there. The next day, it said this, that the tracking station would be a TV link. The post office tried to usurp us and tried to convert. They said, no, we'll take over the thing and we'll use it to do telephony, satellite telephony. Unfortunately, that didn't happen. So Hartbeeshoek was established in 1975. George and then Peter Harvey, who'd now come back from Jodrell, were the two real staff, and then some people left over from the NASA days, and Mike Gaylord then joined from Rhodes. 20% of the time was allocated to Rhodes. And it was, Hewitt says this must be a national facility. This must be for the use of South African universities. So briefly, 50th anniversary of Hart next year. Briefly, going back to Rhodes, 1980. So the senior students at that time. And there's some notables here. Pete Mountford was my predecessor. He did the control system at Hartbeeshoek. Claire Flanagan, the first woman radio astronomer in South Africa. Andy Greibichot, or these days Glitz. More about him a bit later. Graham Obram, who'd done the control system for the 22-meter dish, taught me about control systems. Gerard Diaga, Eddie, Jack Gledial, Graham Poole, the meteor guy, and George, of course, me. But we then went and started doing stuff with Rhodes dropped its own program and started working at Hartbeeshoek. Just need to put in Sandile here. Sandile did his MSc and PhD with Graham Poole in meteor radar studies. He was the first black South African with a PhD in space science. And if you look at his career now, he's done some really fantastic things. Early Hart developments, we had to know the place was kitted out to be a real radio telescope. George drove a lot of this. Spectrometers being put in, new back ends, and of course VLBI. And really, George was the great driver behind all of this. It looked like a real radio telescope. It had chart recorders and modern computers and teletype machines and a VLBI recorder. And yours truly used to sleep there. What science did we do? Is all opportunistic science. What would you do with a small radio telescope in the Southern Hemisphere? We would map the whole sky. And that was something that some students and I did over many, many years. Andy was involved in there again. Pulsar timing. Claire Flanagan did some fundamental work on Vela using the telescope, and later Sarah Buchner took that on. Spectroscopic work, starting with Mike Gaylord, worked on recombination lines. After doing some work with Jim Cohen at Jodrell, we got into masers, OH masers, and then methanol masers. So Charles Miller and her then supervisor, Johan van der Walt, and Mike, did some really fundamental work on this. And continuing George's work on monitoring compact sources and Socinus. George has worked on Socinus. He said to me yesterday, he is going to now finally finalize this paper on 56 years of Socinus data. And I think it was also wonderful that he was an author on the CAT7 paper on Socinus, that really is part of George's legacy, is anything to do with Socinus X1. But of course, the raison d'etre for astronomy at Hartebeeshoek was VLBI. And so George pursued a lot of VLBI experiments with the rest of the world, global experiments, the EVN, and also, very importantly, the Southern Hemisphere VLBI experiment, SHEAVE, with Australia. And then the obvious thing that followed on from that was fundamental astronomy, geodesy and astronomy and astrometry. Axel Notnagel was at the observatory for a while, and others have taken on the baton with that. Later on, we upgraded the telescope more, put on a solid surface. Remember, the dish was initially designed for 960 megahertz. It's now working at 22 gigahertz. We upgraded everything, and again, a little bit of more modern things, perhaps. We put in a new control system. Andy Kraby, or Andy Gotze, as he calls himself now, as he is called now, designed a new control system based on some software that Andy had developed at the ESRF in Grenoble, and it was called TACO. TACO became Tango. Tango is what controls the SKA telescope today. Andy was the architect of that. Phil will know Andy very well from his time at Max Planck. And oops. Yeah. South Africa got involved in the EVN, and Jive took a while to actually join formally, but we did. But during a board of directors meeting at Hartebeeshoek, the then director, CEO of the NRF, Kgotsomekele, another hero in the piece, persuaded Roy Booth to take over directorship of Hartebeeshoek in his retirement, and that was a fantastic thing. John Quick has pushed VLBI at Hartebeeshoek on the technical aspects over the years, and you now have a slate of radio astronomy directors at Hartebeeshoek. There is no director of Hartebeeshoek anymore. So there's myself and Roy and Mike and George. There's another diaspora that needs to be sort of spoken about as well. The people who were South Africans who went out there. Tony Reedhead went to Cambridge from Wits, and then on to Caltech. Skirts did his PhD at Rhodes, went on to Iowa, worked on the magnetospheres of the planets, and in pioneer data in particular. Bernie, no need to mention Bernie just at the moment, perhaps. And then if you go to the physics electronics picture in 1981, we see Athol Kemble and Andy again, who in the lineup, who went on to do things in radio astronomy. So of course Bernie, Van Roth and Riley. There's the citation record. Who else could match that? Then going on, the white paper of 1996, for South Africa had just become a democracy, and Rob Adam was Deputy Director General of what was to become Science and Technology, but basically said, we want to do astronomy in South Africa because it's important for us. And those words stuck. In 2001, SALT groundbreaking had just happened. And Khotso said, and Rob said, we need another big project. Shall we get involved in the SKA? Well, they suggested to me, you look into this. I wrote some emails to people. People came back and said, okay, that sounds like a good idea. And the next thing, I was in Berkeley at the ISAC meeting that happened in 2001, looking like a deer caught in the headlights. ISAC came here to Cape Town in 2004, but a steering committee got put together for the SKA, and there's the sort of five musketeers who were involved: Bernie, Rob, Kgotsomekele, George, and myself. We went to Cabinet. This was my very first PowerPoint presentation I gave to Cabinet, and they said this is a good idea. We had a good site, we said. We could protect it with legislation. And I said, Bernie, let's build it over there. We got involved in the site bid. had 2 site bid teams because there was a double process. We wrote a lot of documentation, and there was a site outcome. And on Africa Day, the announcement was made that that MID would come to South Africa. We needed a technical team because also we were told, now you have to build Meerkat. Where did we get the technical team from? All the yellow background names that I had beforehand: Mike Ings, Dirk Baker, perhaps myself, Mike Gaylord, George Nicholson, and then my students, including Adrian, sitting over there. And that was it. So, we did have a technical team. Here's the early engineering team, all acolytes of either Mike or myself. So, it was a small start, but we had good people to start off with. Meerkat KSB, some of you are sitting around that table, I think, that defined how we would build Meerkat. My boss there, Robert Lang. Incredible collegial partnerships. People really came to the party and helped us in everything we did. And again, you'll recognize some of yourselves sitting around those tables. We built XDM and Cat7 prototypes. We built foundations. I had to put the slide in because there's Tony and there's Phil and they're talking later. We inaugurated the telescope. Fantastic image on the day that we inaugurated the telescope. We were a founding member of the SKAO. And mid-commencement has started, and we've put the first dish up on site for SKA. So I said I'd rush through the end. But we needed more people. We started off with these 5 people. How do we grow them? So we had a human capital development program. Apartheid had stopped South Africans, the majority of South Africans, from engaging in science. We had to overcome that. And we had this intervention to do that. And it started off as what we call the Research and Technology Collaboration Center. And we have the Human Capital Development Program of today. And we have a large radio astronomy community today, about 100 times bigger probably than it was when we started. And that's been a great success. There's a new diaspora. We've now bring people into other places, NGVLA and DSA 2000. And yeah, so that I think is the history. Thank you very much.
So we have time for just one very short question. Anybody in the audience wants to make a short question? No? Then let's go to the next speaker. So Professor Roger Dean should will tell us about the development of SCA. Okay? Oh, sorry, Meerkat. Sorry about that.
Not quite yet, Meerkat. Thanks very much. It's an absolute pleasure to be here and to be talking about this remarkable telescope, Meerkat, that I owe so much of my career to the development towards this. It's impossible for one person to really capture everything that has been done and achieved thus far with this. So I have to, at the same time as I thank all those wonderful contributors that are listed there, I have to state my authorship bias as well. I apologize in advance if I miss out on a few things. Right. So this is a photograph I took with my phone on Inauguration Day as we were taking off, having spent a wonderful day, probably a day I'll never forget, inaugurating the inauguration of this telescope. You can see antennas, these 13.5 meter antennas spread across about 8 kilometers in the heart of the Karoo, more clustered in the center to this sort of pinched core configuration to optimize some pulsar searches and below surface brightness sensitivity. And as you all probably know, we've got 3 receiver bands between 0.58 gigahertz up to 3.5 gigahertz in 3 separate bands. Collectively, this is about 110 meter dish, so a sort of GBT scale SEFD, but of course all the advantages that an interferometer brings, angular resolution, etc. You've got about 2.6 terabits per second going into the F engines, B and X engines, whereas writing to archive for a typical observation, you're getting about a terabyte per hour. And of course, this will be extended by 14 dishes out to 18 kilometers, and I'll come back to that a little bit later. And then, of course, as we heard in the SKO session, merged into SK Mid towards the end of the decade. Justin just showed the slide, but just a huge part of the success is the enormous support received from government over many science ministers, and I think that's testament to the fantastic SORAO staff over the years. This is a timeline, an incomplete timeline of major milestones alongside the Meerkat project, but as you saw with Justin there, the first formal offer to bid to host the SKA back in 2005. The first dish in Meerkat dish in 2014, inauguration in 2018, and that amazing image of the Galactic Center to today, where we get roughly about one Meerkat paper appearing on the archive every 3 days. Now, as anyone who's familiar with the Meerkat project will know, alongside that on the same timeline has been this incredible building of a large radio astronomy community. Justin just took us through 65 years. But I think, thanks to him and others, the last 20 have been just remarkable in how that's grown. That's the number of SORAO grants awarded per year by SORAO, everything from undergraduate scholarships, technicians, all the way to SKA chairs like I hold that support 18 students and postdocs. There are a huge number of highlights to go, and I just simply don't have enough time. And there are other SORAO staff members that would give you a better rendition. But I do think two engineering highlights are the success of building this engineering demonstrator, the CAT-7, which was supposed to just be an engineering demonstrator, but ended up doing a whole lot of science as well. And then the bold change that Justin obviously was a key person behind in changing to offset Gregorian. You can see the side, the optical design, and you can see the side lobes significantly lower. And one of the reasons why we see these beautiful HST quality kind of images, not quite in resolution, but in complexity, as you'll see in a moment. All right, so I'll give you an overview of the Meerkat science program. Unsurprisingly, by design, a lot of this covers the SKA science program, looking at the evolution of galaxies out to cosmic noon, AGN, and star formation. There's a lot of work going on large scale structure, and I'll touch on that in a bit. Obviously, gravitational tests, stochastic gravitational wave background, as well as looking for the holy grail of a black hole pulsar binary. And then what has been a huge push is the unknown. A whole lot of serendipitous science that we've already found with Meerkat, and so much more to look forward to with SKAO. A quick breakdown of the science program. So as was the trend, this was aligned with the survey-driven focus of modern day radio telescopes serving large communities. So 2/3 of the time goes to large survey projects, some of which are wrapping up now. 28% to open time, and it really is open to anyone in the world to propose, and then about 5% to DDT. And you can see in the next bullet there just the enormous increase in demand for this telescope since its first completely open time call in 2020, where 113 proposals were received, to this year where over 200. You're looking at an oversubscription factor that continues to grow, is well over 4. And if you compare that to VLAA configuration time of order 3.5, this is a telescope in demand. And it's in demand with a very international user base. What you see here, this is a slide from Fernando Camilo. You're seeing the PIs of all the OT4 programs, open time programs. So that's from last year. It's a bit of a complicated diagram, but if you start at about 1 o'clock and you move away to 4 o'clock, you can see with the different open time, colorized by different with different colors, and then going into different countries represented by the different PIs, and up to 24 last year. And this is not updated for OT5, but this has increased further with over 200 proposals this most recent year. The science cases, this is the key science of the large survey projects, everything from pulsar timing, nearby H1, deep images of nearby galactic disks, looking at so-called slow transients. I know Rob Fender doesn't like that word because there's nothing slow about them, but some amazing results in the transients domain. And then deep surveys of both the continuum and H1 universe, as well as H1 absorption line work. Then there's the Max Planck Institute for Radio Astronomy's Galactic Plane Survey at L and predominantly S-band in payment for the amazing S-band receivers that we all get to use. And then two Soreo legacy surveys, one of the galactic plane at L-band and one of 115 galaxy clusters. This is the deepest image at about 1 gigahertz of the extragalactic sky at arc-second resolution. It's of the so-called deep 2 field. It was specifically identified to be devoid of very bright sources nearby, and it pushes down to 550 nanojansky, really into that sensitivity domain that the SKA was always aiming to push down into. So you've got constraints on the star-forming population because the majority of the faint sources here are star-forming galaxies at high redshift following the far-infrared radio correlation, basically down to 250 nanojanskys using a traditional PFD analysis. Incredibly deep results. Over larger area, this is results from the MITI collaboration led by and the processing led by Ian Hayward. This is not quite as deep, pushing down to about 2 to 3 microjansky at L-band, but covering a larger area, about a factor of 10 larger, out to 20 square degrees. And this targets very, very well-studied multi-wavelength fields. So there's a wealth of science that's coming out. You'll see that the MITI survey has been very, very productive and producing a lot of great results on the evolution of AGN and star-forming galaxies over cosmic time and environment. This is a survey that I lead with Joaquin Vieira, where we're utilizing the synergy between centimeter wavelength telescopes like Meerkat and millimeter wave, and we've covered 100 square degrees down to about 10 microjansky in just about 120 hours of time, thanks to the heroic efforts of several of my students. But this speaks a little bit to the incredible, not only imaging fidelity, but the survey speed of the Meerkat UHF receivers. So if you zoom in here, you're seeing we've got of order 250,000 galaxies in this 100 square degrees, which obviously has deep SBT coverage. So SZ selected clusters and bright sources, point sources, positive detections, which tend to be these very high redshift star-forming dusty galaxies. For some reason, my slides are not. Oh, there we go. It's back. So if you zoom in, and there's just a wealth of science doing probing this kind of area, that kind of depth, with the imaging fidelity that we have. Got some kind of lag. There we go. So it's not just extragalactic sky. There's been an incredible survey, Thundercat survey, and now gone into what's called XCAT of relativistic jets, not in the far universe, but in our own galaxy, finding some amazing time-resolved topics. Justin mentioned Cassinius X1. There's Cassinius X1, the natal supernova remnant, and a hole being punched through the top right of it. As you can see, the top right there is this. I'm nervous. There we go. I didn't switch it off. Amazing to see that, and through imaging fidelity. Then some relativistic jets in a globular cluster, and then also very, very highly relativistic jets in these stellar mass objects that are just stellar mass black holes, which is just pretty remarkable. H1, I've apologized to H1 enthusiasts in the audience. I haven't given perhaps as much attention as it might, but I did that because or didn't do that because there is an IAU Symposium 392. So I urge you to check that out later this week. But really some amazing results coming out in the H1 sphere. Some highlights, this is a paper that is currently under review, but the Cosmos field detecting a whole number of H1 galaxies below redshift 0.1. The first H1 mass function of an interferometric instruments sort of blank survey. And then, of course, the Meerkat absorption line survey. This is the famous gravitational lens, PKS 1830. And it's detecting, it not only detected H1 and OH absorption of the main lines, but also the emission in one of the satellite lines, which is a redshift record. What should I point at? There we go. This is an interesting application that wasn't really on the cards at the start, but Mario Santos and his team have been championing this approach of H1 intensity mapping, covering large areas of sky by driving the telescope very rapidly, so five arc minutes per second, using it in its total intensity mode, so using the autocorrelations in combination with the intrametric data. And they're covering areas that are covered with rich multi-wavelength coverage, so they have the redshifts, and so they can do the cross correlations with their total intensity map, which is pixel sizes here of order 0.3 degrees, and they've already detected a cross correlation with the Wiggles Z galaxies and Mierklas L band for H1 at redshifts between 0.4 and 0.459. So their ambitions are to go to about a pi steradian and to actually measure BAO as a function of redshift using the H1 line. I'm sure you saw Bernie's amazing talk last Thursday, but and he talks about the serendipity machine, and I always think that Bernie's talking about an algorithm or specific suite of algorithms to find phenomena. But I think Meerkat itself is a serendipity machine. It's finding incredible stuff, and we could give a whole talk just on that. I think one amazing example is this finding through the image domain search a long period pulsar, 76-second period, and you can see the pulses just popping up here. And this is an image made with it and without. So if you look at a P dot diagram, you see this is appearing in a very interesting part of the parameter space, not necessarily designed, but discovered because Ian saw something strange. Another cool example is something that Oleg did. This was essentially, if I'm correct, it was supposed to be a PR stunt. Look at the great conjunction between Jupiter and Saturn. As you know, Oleg's a bit of a wizard, and he was making images of this, and you can see Jupiter and the magnetic field lines. It's not only a beautiful demonstration of the snapshot capability, but he found a galactic transient, which he calls a rat parrot, which you heard of in Justin's talk as well. And I urge you to buy Oleg a beer to tell you more about this galactic transient. But it's how remarkable that in a few arc minutes of area, you're seeing a solar system object, including one of its moons. You're seeing a galactic transient and a distant Fanarov-Riley FR2 object. Quite extraordinary. Mpati also gave a wonderful talk on Thursday. It's quite hard to follow up on all these, but this has not been seen before. This is this very thin kiloparsec in width collimated synchrotron thread connecting the radio lobes over 80 kiloparsec. It's not been seen, and it's got the theorists scratching their heads. I'm not sure that we've got. I haven't followed up with the literature, but I don't know if we have viable options for how this formed exactly. And Mpati was looking. She was wanting to look at one of her H1 jellyfish galaxies, and Sper Marcattini convinced her to put this at the phase sensor so that he could calibrate it out better and look at what came. Another emerging theme is just commensality. I mean, we all knew that commensality was stressed in the design of the SKA and in the precursors, but it's just been remarkable just to the extent to which that is possible thanks to the sensitivity and imaging fidelity. So this is a survey that Kendall Knowles led. It was a Thoreo legacy survey of 115 galaxy clusters, and just amazing science coming out of that in terms of cluster science, looking at halos, relics, comparing that with multi-wavelength information that's there, but also at the same time doing an H1 survey of a large chunk of this field. And there's some work coming out, a Rhodes postdoc on that coming up soon. Then near-field spectroscopy of H1. There have been a whole lot of H1 groups that have just been found, including in some of the most well-studied parts of the sky, the XMM LSS field. Extremely rich legacy multi-wavelength data set, and yet this low redshift group had never been seen before. Shilpa Ranchard, a grad student of mine, picked that up. Marchin was looking at an FRB host, and in 4 hours found 49 galaxies at a range of different redshifts, and there seem to be several groups in that. Graham Laurie found this H1 group at redshift 0.04 and that was just from the Meerkat Galaxy Cluster Legacy Survey. So I think an interesting field there. This is one of my favorite objects, and I excuse my bias, but what could you possibly learn about NGC 6240 when it's been studied by every telescope for 20 years? Well, we found a shock. This is adiabatic compression. There's a slow-moving jet here, never been seen before, and it's basically being compressed by a galaxy over here. And there's a nice little shock front revealing some interesting stuff. We even see a color gradient across the galaxy there. We found jets at megaparsec scale at a different position angle to this slowly moving outflow, which, as you know, it's a binary, as many of you will know, it's a binary supermassive black hole with a kiloparsec separation, the two black crosses there. We also found that in H1, it's interacting with a third partner. There's tidal debris that stems off to the bottom here and connects with a neighbor previously unknown. We also have been doing H1 absorption astrometry between the two black holes. So that all that for 4.5 hours of time, object that been studied for 20 years, 2 master's theses, 2 master's students publishing first author papers. I think there are many examples of that. This is just, my biased view of one. So let's move on to new frontiers. And obviously, as you saw with Ryan Shannon's talk last week, just incredible results coming out of MeerKAT here. So essentially, they've performed a MeerKAT pulsar timing array, 83 millisecond pulsars, predominantly over the southern hemisphere, looking at the correlations between the residuals in the modeled arrival times of this group of 83 pulsars. And the results are pretty startling after just 5 years of observations when you compare that to the length of time that other pulsar timing arrays have been exploring the sky. So this is the correlated amplitude between the timing residuals between those 83 objects, different millisecond pulsars, and that's the angular separation. What you see is clear correlation with what you expect from a heading down curve of this quadrupole nature of the stochastic gravitational wave background. Simply incredible, but further still is rather incredible how Ryan shows the increase in the signal to noise of this MeerKAT pulsar timing array. So we're going to continue to see amazing improvements of that and really a completely new frontier. So that's using an array. Another interesting thing that Ryan showed was looking at just one of these pulsars, looking at the time. He calls this the best pulsar. I don't know enough about pulsars to tell you why. Maybe it's just the level of the residuals or how well behaved it is. But he shows Parkes data over 10 years, and then he shows his MeerKAT data of the last 5, and what he believes to be a continuous gravitational wave. Remarkable stuff that's coming out in comparatively short periods of time. Just truly a multi-messenger facility. I think another area that I'm going to bring my bias to, but I think there's going to be an OH megamaser renaissance or revolution, but that's I'm arguing that because if you look at the Luduma results, it doubled a redshift record that stood for 20 years. 2 years later, MIGHTY tripled that redshift record. And then results coming out from a graduate student of mine, quadrupling that redshift record of megamasers in the universe, which are obviously important as they're some of the most dust-obscured star-forming galaxies in the universe. So getting spectroscopic for redshifts for that is not easy. They're also potentially markers for binary or dual supermassive black hole systems. So very, very, very important for many reasons. But here's why I think there might be a revolution. That's the signal to noise of the most distant one after 4 hours. I'm protecting my graduate students' work there by not showing you the axes, but it's roughly about 500 kilometers. This is a less than 8 kilometer a second feature on the other halfway across the universe, more than halfway across the universe. Very excited about what we'll be able to do with this with future surveys. I think one of the things that's been amazing about MeerKAT is that really helps it get into the zeitgeist is this sort of I'll loosely call it HST quality images, but images that look like that. It's just startling. It sort of knocks you back. It pops out, and there is so much science that you can do with that. In this case, this was a Bill and Satish Thorat led this observation where this was a so-called X-shaped galaxy. The thoughts are that it may be a binary supermassive black hole merging, changing the jet axis, but this pretty emphatically with amazing imaging fidelity and these young jets here, and then also what I'm not showing are the magnetic field lines that sort of turn the corner showing that that's not the case. It's a hydrodynamical backflow. But this is kind of what gets you onto, the New York Times. Another beautiful image by Jim Condon et al., showing all sorts of interesting features that probably don't come out as well here, but learning interesting things. Of course, the most iconic is the image that Meerkat made of the center of our galaxy. That was the inauguration image, but of course there was great science that came out of this. This is the first Meerkat paper in Nature, led by Ian Hayward, of this bipolar outflow of 430 parsec in size. It's thought to be energized by a star-forming event, which is probably the cause of the energizing of these numerous filaments that Meerkat has discovered so many more of. But it's an incredible image. I mean, people have shown this over and over. So what is there to say about this? For me, personally, at the time that Jansky was sort of mapping this radio excess towards the center of the Milky Way, and at the time Reber was making improved maps thereof, that was the sort of the peak of the surrealist movement. And for me, this radio image, this science image, is nothing short of a surrealist work of art. I mean, it's got everything about it: the ethereal nature, the contrast and the circular features, and these linear, sharp features, the explosive nature yet stationary. It's truly, I think, an image that belongs in modern art museums, as well as along with the EHT image. And if you'll give me 30 more seconds just to indulge me for a second, it also does make me wonder who else has a view of the center of our galaxy that is quite so remarkable. Is it just us? Which, at the same time as Reber and Jansky were kind of doing this work, there was a famous writer called Ernest Hemingway writing, and one of his masterstrokes was masterpieces was The Old Man and the Sea, and talking about, he only really knew loneliness when he was wrestling that marlin, and he was way more lonely than he'd ever been. Are we indeed alone? Are we the only ones that see that amazing view? Well, there's a program on Meerkat led by Breakthrough Listen that is looking at hundreds of thousands of stars to test exactly that through very, very powerful compute and smart algorithms at the back end, using this flexible ability to bring user-supplied equipment, and which I think was a very smart design decision from the start from the Meerkat team. And if you just look at what they're covering, well, surely this is an incredible search for that needle in the haystack. We're moving ahead to Meerkat Plus in the coming year and a bit. As I said, adding 14 SKA dishes with L-band and S-band receivers out to 18-kilometer baselines. And we had a science workshop at WITS last year to discuss some of the amazing science and that step towards SKA mid. There is ongoing efforts to Meerkat VLBI. And it's interesting what Justin showed, that slide 51 years ago, the first SA Effelsberg baseline fringes, and there are fringes with Effelsberg and Meerkat. And Marcel Goos at Soreo is leading this effort and doing some tremendous work. So we hope to see that is added, and hopefully it might be as transformative as ALMA VLBI has, certainly for Event Horizon Telescope work, where it makes the whole network more robust with the added signal to noise. My PhD advisor, Steve Rawlings, is always credited. Justin tells the story of how he says about Meerkat, build it and they will come. Talking about the amazing scientists that have come and done fantastic science on Meerkat, growing that South Africa into that global community once again. But I don't think anyone could have predicted just how impactful it would be for building the scaffolding for so many brilliant young students to climb and seek just exploring the universe and developing amazing skills inspired by this instrument. And I just want to acknowledge that. So there's a summary. Meerkat is, I hope I've convinced you, delivering a wide range of transformational science. it certainly seems like commensal and serendipitous seems to be the new norm. But we're only getting started. It's a very hungry community that is beginning to mature, and its reach certainly exceeds its grasp in my perspective. And so the future is bright. We have Meerkat Plus on the immediate horizon, SKA VLBI, and some of the amazing synergies that we'll see with millimeter observatories, as we'll hear in the next talk. So thanks very much.
Thanks a lot. Beautiful talk. I've had the chance to meet one of those students, and it's amazing the revolution you are driving into the young population. Congratulations. So any questions from the audience? No questions? I can't believe it. Okay, so I was impressed about these high resolution images. It's amazing. But we had just in the session before, a talk about polarimetry. And so which are your expectations about what Meerkat will do with polarimetry?
Yeah, so this is one of the areas, I'm sure the many areas that I left out, partly because of my lack of experience with polarimetry. But there have been a whole lot of tests. I think Ben Hugo's work on lunar polarimetry and the wealth of science that he's doing there has been hugely interesting. Mighty has just put out their first results on the in a subset of the L band. There have been some challenges with the full commissioning of polarimetry in the different bands, and I'm not completely up to speed with all the aspects around that. But certainly there's a lot of ongoing work, and I apologize to my friends for giving this less attention than some of the other areas.
Another question.
Yeah, really nice, Roger. So my question is, looking forward for the next 5 or 6 years or so, as SKA mid is, dramatically ramping up construction. How nailed down is it? How much science is going to be happening over those years during the construction and around the construction and with the construction?
Yeah, I mean, this is not. We heard Tracy Cheatham talking about this in the ESCO session on Friday. The ambition is for there to be no interruption. That's the ambition. I don't know if I want to venture into saying much more than that, but there's a lot of close coordination between the teams. It's probably best that a Soraya representative and an SKA representative speak more to that. It's a little bit out of my wheelhouse.
Yeah. Yes.
I mean, I think for Meerkat users, they probably know it's challenging. We have the choice between let's build quickly and get out of there or continue doing science, but we obviously want to use Meerkat as much as possible. So it's a tough balancing act, and we'll continue to try balancing it as much as we can.
Thanks a lot. Any further question? Yeah.
For those of us who are trying to continue or do such work, any idea about how funding can be mobilized? Is there any funding still left in the world for some big projects?
For one of those instruments in general, or funding in general? Look, there's definitely funding opportunities for smart ideas and exciting science. There's no doubt about that. I don't know how else to answer that, but yeah.
Okay, so let's thank our speaker again. And now we have the next speakers, who are Tony. Okay, let me check. So it's Tony Beasley from NRO and Philip Diamond for SKAO. And they will be talking about the synergies between NGVLA
SCAMIT and SCAMIT, basically. Okay, so please go ahead.
Yep, thank you very much. If you could pull up Phil Diamond's slides first. It's good to see standing room only, Tony. I think there are some technical difficulties here.
You are two people in a talk and the presentation was labeled under sanitary risks. So they have just found out and they will go at home.
We could switch orders. Yeah. Take direction from. Okay, you first, Tony. Okay, good afternoon. I'd like to thank the Division B organisers for letting me and Phil give a talk about these remarkable telescopes. What I'm discussing today is the Next Generation Very Large Array. Over the course of 70 years, NRAO has run a series of incredible instruments that have served the global research community. The VLA in the last 10 years has served people from 80 countries, more than 12,000 astronomers. And with these instruments, we have really tried to support the entire global community in terms of radio astronomy. The VLA is 44 years old. And so, it has come along during the 70s and 80s. We have done one upgrade of it. But just in general, it is still a remarkable telescope. But to get to the next level of science, more is required. And of course, part of that science dream is what has motivated the SKA to move forward. What I'm going to talk about today is the Next Generation Very Large Array. And the concept here is to build an instrument that has 10 times the sensitivity of our existing instruments, combine the VLA and the VLBA, expand the frequency range of coverage of the instrument. And the way to do that is to build more antennas. This is the technical, oops. Go back. Okay, there we go. This is the technical baseline here. What you see is there are 244 18-meter diameter antennas. These are distributed, a lot of them in the plains of St. Augustine, about 190 of them are. The remainder are spread around the desert southwest and eventually linking out to the VLBA, and I'll show you the configuration in a minute. There's 6 bands, which we have imaginatively described as bands 1 through 6, like every telescope does. Our bands are different to everyone else's bands, of course. As we look at the sort of the digital performance, what we're trying to bring back where we can is 20 gigahertz of bandwidth, dual polarization. So that is a significant increase relative to what we currently do with the VLA. This is the 18-meter diameter antenna. This has been designed by our colleagues, MTechs in Germany. And we are building a prototype right now, and that's what it looked like yesterday, I think. What you see is there a laser? Yeah, that's not the dish there. That's the subreflector. What you actually see in the background here is that they're starting to assemble the prototype dish. So this dish will be assembled over the next few months and tested, and then we will move on to considering what we do in terms of production. It's actually, we're reusing the ALMA foundation for these tests. We have antenna variants. There are other parts of the project. Inside the project, we have a 6-meter design antenna, and what you see on the left is a reference design produced by our Canadian colleagues. On the right, you see another design which we are pursuing. It's the same antenna, but it goes to lower elevation, and that's for some particular applications that our Department of Defense friends are interested in as part of partnership with them. Data acquisition and front ends. This is kind of a traditional approach. I mean, most telescopes in this area are using this sort of approach. There are 6 bands. There's technologies involved in this. that we have developed over the course of many years here to really improve the mean time between failure of these instruments. I mean, we can all produce excellent receivers these days, but we need receivers that do not need to be touched for 6 months. Whereas it turns out the average VLA receiver, the average VLA cabin is touched once a month at the moment. So interestingly, that's where some of the difficulty and some of the design challenges. Here's the configuration. If you sort of start up on the top left, actually to start here, this is sort of the core of the array. This is when you move out to sort of scales of the current VLA. This is the desert southwest, and then this is linking out into the long sites. Now, this is not actually our baseline configuration. What we've been doing over the course of the last year or two is exploring different locations to put some of these antennas. Not all of the current locations are perfect for one reason or another, and as things evolve, there'll be other opportunities. This is trying to place it in sort of technological context. On the y-axis here, you kind of see antenna sensitivity, essentially, and then you see frequency. And this is one of those diagrams you produce when you're trying to pitch a project to make yours look much better than everybody else's. And I hope you agree with me. But in reality, this diagram doesn't do service to SKA on the lower side of this, which is remarkable, nor to ALMA, which sort of runs off to the side here. But there is this remarkable niche here where NGVLA will sit neatly between SKA and ALMA, and those will be the tools that our community will have available for our research. Same kind of here, when you look at the combination of the short and the long baselines, producing an instrument that can actually address all those spatial scales, you produce, again, another lovely looking diagram. So the science case for NGVLA, I will not go into detail. Unveiling the formation of solar system analogs is, kind of a key one. Astrochemistry, charting the assembly, structure, and evolution of galaxies over time, pulsars, and understanding black holes. This is a particularly attractive one. This is where you're actually looking to see planets forming around nearby stars. Now, you cannot detect the planet. You can detect the nebulae of gas around those planets that are forming. And given the timescales here, you can actually image them. And so these are the types of movies that NGVLA will make in years to come by sampling these systems on kind of a weekly or monthly basis. So in the first 10 years, there'll be movies of planets. We will do a lot of astrochemistry in terms of looking for organic molecules in protoplanetary disks, imaging cold molecular gas, detecting some of those pulsars we all talk about at the galactic center, and then doing a lot of the gravitational wave and multi-messenger science, which is going to be very popular, will continue to be popular in this coming decade. Okay, in the decadal survey in 2020, NGVLA was ranked as a high priority with kind of the marching orders of being online in the middle of 2030. So that's going to be hard. For those of you that are sort of aware, the US astronomy pipeline is complex at the moment. And so these projects moving forward, any of the decadal survey projects moving forward has sort of been interesting. So we are banging away on that. We have our conceptual design review with the NSF coming up in a couple of weeks' time. In general, we have a lot of input from the community. We have advisory committees and an international development consortium. This image here is from a conference that we had back in May of last year, where we actually our SKA friends came together to look at the science opportunities if both of these arrays were possible. What could we do? What were the synergistic activities and so on? That was an excellent conference, and there was a lot of amazing science that was discussed. We have many good partners, both in the US and international communities. So in summary, the project and its broad science case and technical plan has good support. And we are trying to capitalize on other investments in the community and really push a new dimension in centimeter radio astronomy. The project design and prototyping is underway, and we've got some major milestones in the next year. The prototype will be a big deal. A construction decision is no closer than 4 or 5 years. And so there's many miles to go here. But there are a lot of amazing synergies with SKA and ALMA. We look forward to exploring those. And NRAO and AUI are proud to bring this forward for consideration and hopefully add this to the arsenal of instruments we have available in the community. Thanks.
Tony. Okay, then we will ask for the questions to the two at the end of the presentation. Go ahead.
Okay, thanks, Tony. I'll talk a little bit about the SKAO and then talk more specifically about some potential synergies that Tony and I discussed earlier. So just to put the SK Observatory into context, we're an intergovernmental organization, a very young one. We're just over 3 years old, much younger than European Southern Observatory and other intergovernmental organizations like CERN or ESA. And our mission is to build and operate the world's 2 largest radio telescopes. You see the membership there, with countries moving through government decision to the accession stage to become members. And what I'm very pleased to say is that just last week, the law was passed by the German Parliament, the accession law to the SK Observatory, and it's waiting for the President of Germany to sign it. He's not available. My suspicion is he's in the Mediterranean somewhere enjoying the summer holiday. But that's my impression. That's probably not the truth. So what are we building? Well, we have this mantra: 1 observatory, 2 telescopes, 3 sites. So the headquarters are at the Jodrell Bank in the UK, where you see a very typical day in the northwest England. And the 2 radio telescopes, SK Mid here in South Africa, which ultimately will be 197 dishes, incorporating Meerkat, as you heard from Roger earlier, and the Meerkat extension. That's very much part of the plan, and you'll see the construction status in a moment. The telescopes will be spread across 150 kilometers in the Karoo, and provide fantastic imaging capability. Meerkat is already doing wonderful things, but if you take it to 197 telescopes, it's well, NRAO have a similar plan, obviously. And then for SKA low, we will not have dishes. We'll have the low frequency antennas in Western Australia. 131,000 of these distributed in 512 stations across 75 kilometers out in the remote parts of Western Australia. Both sites selected specifically for their radio quietness. Our construction cost approximately 1.3 billion euros, and we intend to be operational by the end of the decade, generating enormous amounts of data, which is a challenge in itself. So these are the array configurations: 3 spiral arms, logarithmic spirals, with a very densely populated core region. For those of you who've been out to the site, either at the weekend or on the flights that were arranged for some last week, you will see how densely packed the core already is with the Meerkat dishes, with the SKA mid dishes being constructed around them. And a similar extent, a similar configuration in Australia on the right there. We're prototyping and intend to build renewable power stations for both SKA mid and low. And you can see in the bottom right here the first prototype system that's going to go out on one of the spiral arms of SKA mid for testing. There is grid power in the Karoo, but not enough. So we are going to have to extend it. And in Australia, there is no grid power. We've got to bring everything with us. But we're building on the CSIRO ASCAP power station that's already there. Data processing is interesting if you just look at the size of those numbers. So here in South Africa, we'll be transmitting 20 terabits per second of raw data over 800 kilometers of fiber to the central signal processor, the correlator beamformer, which won't be at the telescope, it'll be in Cape Town. And similarly, its equivalent will be in Perth, not out at the site. Modern communications technology allows us to do this. We'll then have 2 supercomputers, one also in Perth, one also in Cape Town, adjacent to the correlator, which will do the calibration and generate the SKA data products. Normally, the supercomputers sit to the right of the telescope boundary, but for us, for the SKA, they sit inside the telescope boundary. They're an integral part of the radio telescope. And so the data will be distributed globally to what are called SKA regional centers. And that is how you, the astronomers, will access your data through these regional centers. You won't generally interact with the supercomputers. The regional centers, we have a program underway now, which is producing the initial development, and we'll roll them out over the next few years. It's a federated global network, which, as I said, will provide the user data access. This is somewhat similar to the CERN grid system that was set up to process Large Hadron Collider data, but actually the data volumes involved are a factor of 10 or 20 larger than those of the LHC. Science, the science case was generated some 10 years or so ago by our science working groups. We're updating it next year. Science moves on, as we all know. But these are the broad areas that are being that the SKA will provide capability for, and it is truly an enormous range of science. Current status, well, we're building the observatory up from scratch. I was employee number 12, but when I arrived, there were only 8 of us because some had already left. So we started basically from nothing, and we're now up to 300 staff, ramping up to about 450, distribution across the 3 sites, as you see there. We're somewhat over 3 years into the construction. Let the large majority of construction contracts and have committed a huge amount of money for the construction activities. And just a few pictures to show you how that money is being spent. I like this picture because it's at the core of Meerkat, showing SKA Foundation being prepared. But it shows one of the challenges that we're building SKA Mid in the center of a working radio telescope, Meerkat, which is producing wonderful science. And so we're being as careful as we can to avoid impacting the Meerkat science. But inevitably there is impact. We can't avoid it. And as was just alluded to, at some point there will be a full integration process of Meerkat into SKA Mid. This is a picture from the 4th of July of this year. This is the very first SKA Mid dish being constructed. This was the reflector surface being lifted onto the pedestal. We have 2 more dishes on site, a 4th, which was actually the first built at the factory in Shizhuang in China, and a whole production line producing dishes which are traveling the 16,000 kilometers to the Karoo. In Western Australia, this is, again, I like this photo showing the trenching for the fiber and the power that's going in. This shows a very easily dug trench. We have hit granite in some areas, and that's a little bit more challenging. Some big machines been brought in to deal with that. We expected to hit it, so it's no surprise. But we have the first, in fact, we have 4 stations now complete, but these are the first 2 stations complete. And we're already testing and commissioning the first 2 stations, only 510 to go. But you see the ground planes laid out for 4 other stations in this cluster. A lot of stations outside the core tend to be in clusters of 6. And I always worried that dishes would be more photogenic than log periodic antennas. But actually, when you're standing in the middle of a station with these 2-meter tall antennas, my friend Tony here probably be as tall as an antenna. I'm less so. It really is an impressive sight. And just to think there's going to be a forest of these in our core. And the numbers involved are dramatic. Just for SKA Mid, never mind low, we're building 450 kilometers of road, 650 kilometers of fiber being laid, 250 kilometers of power cables, and 109 dish foundations. So it gives you some idea of the scale of the construction that's happening right now. And very nice milestone, which we released on just late last week. It's a small but important milestone. It's the first 24-hour all-sky image from the very first SKA low station. And you can see, you see the sun there, which dominates, of course, the contrast of that particular image. M87, Centaurus A, the galactic center coming up, and you see the galactic center pass overhead. So, synergies. Well, NRAO is, I used to work at NRAO, 12 years there. And to my mind, it was one of the best places to work in astronomy. They were an incredibly open organization, still are an incredibly open organization. And we're the new kid on the block, SKA Observatory. But it's always been my intent that we adopt that same philosophy. So I'm very pleased with the collaborations that we have on the development of technologies and software. We're working together in different avenues. NRAO has to deal with the US system. We, the SKA Observatory, are able to be much more embedded in the international system. But we work together and we share information to address the issues of spaceborne radio interference. We have relied upon experts from NRAO and the broader community to sit on our review panels. What's very pleasing is that we're now being asked to sit on NRAO's review panels, which I think reflects the maturing of the SK Observatory. Tony mentioned the very nice meeting we had in Vancouver last year. We did have not a science meeting, but a meeting in Reykjavik. Was it 2019, Tony? Something like that, pre-COVID, where NRAO and NSF representatives and SKA pre-treaty, but the SKA organization got together to talk about items of mutual interest. And in fact, one of the action items coming out from that was to organize a joint conference, which we did in 2023. I should say that I don't know if you've been to Iceland. It's a very expensive place. And Tony pulled a fast one on me. He said, I'll pay for the venue, you pay for dinner. And that was a wise choice. It's a very nice dinner, but it was a very expensive dinner for the group. Then we've got future synergies. We want to continue, and I would like to see formalized in some way, joint technology and software development programs. We all know astronomy software has its challenges. And I think between us and working with colleagues at other observatories, Astron, ATNF, Soreo, and other places, I think we can join our forces and have a multiplier there. Then I think we've got to look at these future science synergies, fully exploit the north-south hemispheric coverage that having the telescopes in the two hemispheres will bring. We should talk about coordinated observing programs. And we could also even consider a joint or very similar observing proposal process. One key element is that one person who led the ALMA observing proposal process also works for SKAO. Now, whether that we are going to end up as similar as we might is still to be determined. But it's things like that where we can assist the community. And then I've left it open as to other areas. I think it's too early yet to say if there might be stronger synergies, but I think it's definitely something, Reykjavik 2.0, but maybe somewhat cheaper, that we can actually sit down and explore what the future might look like. So thank you all very much.
So, time for questions to any of our two speakers. So, okay, first over there.
Nice summary by you both. Let me ask, alas, not about a science question, but how we do the science. Tony alluded to mean time between failure. And so how do these telescopes are completely new scale to us. So either Phil, what are you and SKO helping Tony and NRAO understand about how to build systems that are robust so we're not falling behind the curve of fixing them, or vice versa, Tony, in terms of receiver design, NRAO informing SKO about making sure these telescopes continue working at full capability all the time?
Well, so I'm probably not the right person to answer that in detail, but as you've just said, Joe, the scale of these instruments different from anything we've known before, and we can't, as Tony indicated, have as happens at the VLA, where people have to go out and deal with issues on the telescopes once a month. I think Meerkat with 64 and presumably ALMA, much more complex systems, have been looking at this. In our design process, we've very much been looking at mean time between failure and how we simplify systems to minimize that happening. Of course, we, SKA that is, have not yet deployed any of these systems. So yes, we can build it into the design process, but we've got to see how it works in practice. Tony.
Well, a lot of the activity of the antenna is about cryogenics. That is often the reason you were going out there, and so that's an area we've just put some research into. There's a new style of cryogenic cooler that we're trying to develop. I think it is true, certainly on the software side, that there's a lot of synergy in terms of algorithm development and all that. On the hardware side, there's not a lot of overlap with low per se, but certainly with mid, as Phil says, we're sitting on each other's reviews, and frankly, anything we have is available to the community for people to implement and so on. So I think there's plenty of exchange there, no secrets. Yep.
Okay, question here.
Yeah, I love to see talks like this and the fact that you guys are talking and hopefully the observatories are talking. On the same vein, the new kid on the block, maybe DSA 2000, different scale funding wise, but have you guys thought about potentially ways of opening and bringing potentially them into the fold, discussing scalability and reliability issues and stuff like that you all have in common with DSA 2000?
I'll go first. So we're about to sign an MOU with DSA 2000 to sort of pursue some joint technology ideas. Again, it's kind of the same thing where a lot of our people have been sitting on their reviews and vice versa and so on. I would say once again, if you look at the design of DSA 2000s, the antennas up front are kind of different, the way that's being done. And then in reality, the way the data is being processed up back is kind of different as well. So the types of areas we've looked at collaborating on are things like archiving and maybe image formation and things like that. So I think the answer is yeah, but DSA, very exciting. It is a little different from what we're doing in some ways. Yep.
Any other question? Yeah.
Hi, thanks very much for the talks. For the SKA, we've heard a lot about the Science Regional Centre approach to handling the 700 petabytes of data per year that's expected to be produced and given to the SRCs. Is there a similar scale of data, a challenge for the next generation VLA? And if so, are you also taking a Science Regional Centre type approach?
So there is the same kind of scale of problem, sure. But the approach we're taking kind of with data is much more aligned with what we've done with ALMA, which is that the deliverable from the instrument is a high-level data product that you can start doing science on immediately. So we do not necessarily think that we're sending a whole lot of visibility data out to anyone. most of the processing of NGVLA data will happen in NGVLA systems. Now, that doesn't mean it can't be rerun and so on. We are keeping the visibilities and so on. But that is not something that scales very well. The ability for us to send petabytes out to users. I would argue that currently we're sending terabytes out to users, and that's terrible. That is not going so well. So just in general, this is sort of sitting on top of our ALMA experience. The goal is to produce high-level data products. And really, I guess that's what the SRCs are doing. Right? Yeah, please.
Yeah, pretty much the same. We will actually a little bit different. We will not keep the visibilities. They're too large. You saw the volumes of data that we intend to generate. Once we ramp up to that level, it'll take us a while to get there. But no, it's high-level data products that will be distributed. That's the 700 petabytes per year. It's high-level data products going to the SRCs. And we just can't afford to keep the visibilities. The scale is too large. What was the mantra on Friday, Naomi? You can't bring it to your laptop. So we astronomers have to get used to that new mantra. If you're an SKA user, you won't be able to hold the data on your laptop ever. So.
Any further question? Yeah.
So a big new kid on the block as far as centimeter interferometry is concerned is will be China. Could you say something about future cooperation or lack of cooperation with that community in the future?
Well, I can give the easier answer. China is a full member of the SKA Observatory, highly responsible member, fulfilling all of its obligations, and Chinese astronomy community will be full users of the SKA Observatory. Over to you.
I have no comment. It's actually at this conference and just in general, it's hard not to see the incredible progress that's being made in China and all of the instruments that are being built and so on. So we have supported our Chinese colleagues over the years, and we will continue to do that. We've had a series of US-China workshops in recent years, just looking at the opportunities. It's hard for some reasons, and there are areas that we don't go into, but it's impossible to ignore that China has got a lot of instruments coming online. There'll be VLBI opportunities. There'll be all kinds of opportunities. So it's very exciting to hear what's going on.
Further questions? No? Then let's thank our speakers. And this is the end of Division B days today.